renewable. Uh, he is working. He has worked as a senior postdoctoral research associate in Sweden and Norway, and has tremendous publications in 57 peer-reviewed journals, and also 29 publications in as a conferences and book chapters. So I would like to welcome Dr. Vivekanand to give his talk today.
Thank you, sir. Thank you so much, and good morning to all of you. And now I'll start the presentation right away. And what I'm thinking, maybe the presentation timing is for 45 minutes.
Yes.
Yeah. So right now, I think we can start.
Yeah.
Today we will be discussing more in detail about the biogas from variety of feedstocks. And I will be presenting few live case studies, their concerns, and how this production of biogas from the variety of feedstocks could take a decisive role in the area of circular economy. So putting the India on the map at a world level, we see like around 18% of world's population resides in India, and we consume only 6% of primary energy for all these people. And we import oil around 80%, and that amounts to $88 billion per year to the exchequer, that is Government of India. And government has already decided that 50% of renewable energy should be there by 2040. And out of that, I think in India there is a potential from biomass, it's 25 gigawatts, and installed capacity is around 8.1, but a little more as of the current data. But how we can reach and touch this 25 gigawatt, maybe let's say 20 for the realistic figures, it has to be, go through residual resource engineering. And looking at that, if we see in a larger perspective, that it's a 1 year old data. So now currently I think we are 367 or 66 gigawatt. We have a total installed capacity at national level. And from our beloved and honorable Prime Minister, we think that we will be touching 2022, the half of the energy requirement will generate it from the renewable resources in the terms of solar, bio, wind, and small hydropower. And if you look at the last line, in 2003, we have been, having the production of only around 4 gigawatt from renewables. But in 2019, we touched up to 80 gigawatt, and currently we are more than 80 gigawatt at a national level. So there is a tremendous increase in the area of renewable energy. And why I'm focusing more on this, because it's not limited to the bioenergy as per today's talk only, rather than it's more limited for the solar power, biopower, wind energy, and small hydropower stations. Other than that, there are also possibilities in the some of these tidal energy area in the coastal states of the India. Now you must be wondering why bioenergy is important. There are a number of renewable energy resources, but bioenergy has unique feature which can provide liquid transportation fuel, in the sense that you can design a solar car and that will run only once there is sunlight or there is energy stored in the batteries. But bioenergy has the beauty that it can be liquefied biomethane. Already you have bioethanol, already you have biobutanol, which you can, as well as you do have biodiesel, which you can directly use with a little modification in your internal combustion engine. But still there are challenges in terms of the deconstruction of the marine biomass as well as lignocellulosic biomass. We do need robust cocktail of enzymes which can dissolve most of the polysaccharides, as well as efficient bioconversion process. There are pre-treatment and bioprocessing which could work as key technologies in putting all these challenges to a lower tone, as well as we may have the enzymes coming from industry, but we do have to pay the prices for that. Looking at the resources, what kind of biomass or waste can we call them resource? So if you look around the history, biomass is oldest source of energy. We have seen in our homes that mothers have been cooking utilizing solid biofuel like wood, etc., as well as the cow dung cakes, dried ones. All living and element plants, industries, municipal, they generate waste in a huge amount. We do have, as a agrarian country, we do have unlimited supply of biomass, which even in cities or in rural areas, it is used for cooking, heating, and production of electricity. So if you look around, bioenergy, it reduces the emission of greenhouse gases. Like if you put the cow dung just like that, it emits more methane, and which directly goes into the atmosphere. But if you go for its anaerobic digestion, produce the methane and use it for production of heat and electricity, then you minimize the direct release of methane into the environment, which is 22 times more potent greenhouse gas compared to the CO2. So bioenergy is clean and renewable source of energy, and you do have different sectors like agro-industrial sector and livestock sector like cattle manure, pig manure, poultry waste, goat waste, etc. So today we will be discussing more about what are the key technologies or alternatives that are present for waste treatment and what are the most climate friendly options. Is there any separate collection of bio waste is viable? पॉसिबल तो है बट वायबल होना वो ज्यादा जरूरी है. Can it be implemented in campuses like institutional campuses or big cities or mega cities, as well as is there any operational and economic evidences where these projects are going on? Looking at sustainable development goals, participants, hello.
Sir, you can carry on, sir.
Yes. Now I'm thinking if you have any question in between, you can just please stop me and ask. And if I am going, a little fast because of the time constraint, you can stop me and ask the questions anytime. Is it
Sure,
okay?
sir. Yes.
Yeah. So looking at 17 Sustainable Development Goals from United Nations, I think two important goals are there, which are having significant role in today's presentation. They are in SDG 11, and they are 11.3 and 11.6. That is land use efficiency as well as the waste management and recycling. Slowly we will be putting on it simply. So there is a natural resource sustainability. Usually it has been asked that whether it is challenge or not. So life itself is a challenge. So we have to find the solution in our everyday life. Looking at the environmental challenges as well as socio-economic challenges, if you look around in the central rectangle, there is a natural resource, its extraction, its use and disposal. So if we are going to do all this, what kind of economical and environmental challenges we will be having? To look around, in the left elliptical circle, that pollution, climate change, and ecosystem destruction. That's what we create once we try to exploit all or most of the natural resources. Coming to the right one, it's a depletion or shortage. There is a price shocks. There is a import dependence and economic insecurity, as well as there is a conflict over the access at international level. So all this, go for a natural resource sustainability issue and how we can solve these challenges. We do have, 4 options to reduce the use of the same, to substitute them with the non-renewables, increase the resource efficiency, create more with less, as well as go for a circular economy policy where you reuse and recycle the natural resources or anything which is possible to reuse and recycle, keeping in mind that we are not harming the environment as well as the socio-economic system. So moving from extract, make, use and throw model to utilizing waste as a secondary raw material that helps in reduction of and extraction of primary or virgin raw material and associated environmental impacts, including GHG emissions. So if we move around from the resource, production, consumption and waste to the recycling of all these material and reuse them, in an integrated way, it's a circular economy. There is already, a value which is 1.8 trillion euros by 2030 in European Union, where there is circular economy is going to play a larger role. And you will be happy to know that in Sweden, in Stockholm, there is a mall which works on this circular economy basis, where they sell and make all the materials from reused and recycled items. And on the same manner, in India, in Hyderabad, there has a new mall came up. They do sell all these recycled materials in the name of circular economy. So that boosts a common man as well as our own local economy, and with our beloved Prime Minister's terms, Atmanirbhar. So why bio-based economy is important? Because there is a huge amount of renewable biomass available, which can be converted and transformed to the biofuels and biochemicals. Again, the challenges remain same as we discussed in our first or second slide. So looking at waste at a national level, municipal solid waste, then we see like in India, I think if you look around all these 4 bullet points, and it's a little bit disturbing data. Like we generate around 68.8 million tons per year, the municipal solid waste in India, and we are going to produce more and more, like 160 million tons per year by 2041. So it's a huge amount. And out of that, 50 to 57% are organic waste. Recyclables, they are 16 to 19%, and then there is the inert materials. And this, the calorific value of the same is around 7 to 10 megajoules per kg, because we throw a lot of goods, and especially food materials, organic materials, and we are curry and dal loving people. So we throw most of the food materials, and that's why our municipal solid waste has a very lower calorific value compared to the municipal solid waste of other countries. So look around the national data, how important it is to manage the waste as a resource. Like if we have, as per previous slide, 68 million tons per year at a national level we generate municipal solid waste. Out of that, only 53 million tons per year is collected, and out of that 78, only 15% is treated. And now you must got the answer that why our streets are full with municipal solid waste and garbages, because we treat only 10 million tons out of 68 million tons per year. And it's obvious that there will be environmental concerns, there will be health concerns, there will be eyesore, there will be pathogens, there will be rodents, there will be pigs all around, and it's a disturbing figure where we need to tap this potential of municipal solid waste management, and just check the natural resource degradation, climate change, as well as the quality of life. Look around this figure. Top 10 states in India which are best in municipal solid waste management, it's a Chhattisgarh. So they process around 74% of solid waste. Telangana, it processes around 67%. Look around Delhi. They process around 55%. That is also shown in the bold. But if you go around in the left column, bottom 10 states, the Haryana, West Bengal, Mizoram, Pondicherry, Bihar, Orissa, Jharkhand, Jammu Kashmir, Dadra, Nagar Haveli, Arunachal, they process only from 0 to 6% whatever they produce. So it's a quite disturbing figure, and at a national level we need to take a lot of care before we throw our garbage. So why all these challenges are there in our system? Very first thing is the underestimation of waste generation rates, as well as we do have resources which are very borderline. Lack of data on which we can rely and we can update. Lack of technical and managerial inputs, because we treat as a chalta hai ho jayega. So it's more kind of, ad hoc approach where we put some rag pickers to keep it up. That's it. Lack of capacity and resource, they collect and segregate, but once they reach the waste depot, they dump everything at the same site. So there is no benefit basically of segregation. So collection bins are poorly designed and sometimes overfilled. You might have seen in your daily life. Installation locations and poor collection efficiency is there in most of the municipal areas. Storage of waste at source is less or lacking because there is no land, especially in big cities. The prices are very high and municipal uh, authorities can't bear that. So they have to take this waste at least 30 to 40 kilometers away from the main city, which also costs a lot of money. And finally, me and you have to pay in the form of taxes. So how we can, minimize all this and how we can manage it, which is a valuable treasure in coming future. So in the light of Swachh Bharat Abhiyan, Startup India, as well as Atmanirbhar Bharat, you can always go for organic waste management because that is around $8.3 billion in India itself. And we are a growing market. और जैसे जैसे हम पैसा ज्यादा कमाते हैं उसी तरह से हमारा वेस्ट प्रोड्यूस करने का जो तरीका है वो बढ़ते जाता है. You might have seen people in the शादी कि वो खाने पे गए हुए हैं और पूरा प्लेट भरा हुआ है, either they liked it or not, but it's just thrown. एंड हमारे यहाँ ये वाला काम क्लीनिंग का स्पेशली रैग पिकर्स या स्मॉल टाइम कॉन्ट्रैक्टर्स के थ्रू होता है. तो उनका जो मेजर मोटिव है दैट इज अर्न मोर एंड मोर रेवेन्यूज. आइदर यू डू द जॉब और नॉट, it hardly matters. So what are the possible solutions in the form of drivers as well as challenges? We are going for increased urbanization, but at the same time we have been very skeptical for collection and segregation of waste at the source. There have been corporate level industries, government as well as NGOs which take a lot of initiative. Then the problem comes for the availability of land as well as the revenue generation. There is an increased awareness in form of Swachh Bharat, but spreading interest and motivation is again a challenge in a country like India because we are quite huge, 1.38 billion people. So all this, I think we can, go for a centralized database in the neighboring areas. We should hire a well-trained personnel who is really a master, waste management technologies, as well as he do have passion to work for this. We do have to take party of municipal corporations as well as the public itself, address the issue of overall organic waste management in form of biomethanation and production of biocakes, have the least impact on public health and environment, consume minimal resource, and it should be economically feasible. Training programs and periodical follow-up and monitoring as well as surveillance. I think we are very weak, especially in terms of waste management, where we don't monitor and we don't, take the follow-up or we don't send the people for training program. क्योंकि मुझे लगता है कि अपने यहाँ का सिस्टम ही अलग है कि सफाई करना होता है तो माँ भी घर में बोलती है कि राजू बेटा एक गंदा कपड़ा लाना सफाई करना है. So till we don't come up with this mentality, I think situations are going to be more or less same. Possible solution for waste management in a country like India, awareness rising is must. Educational campaigns, recovery of edibles as animal food from food mills. Non-edible organic waste should be composted. Material recovery can go and it can go for biological treatment, as well as landfill and incineration are least preferable because of obvious reasons. So what we are good at, we are doing less composting, less incineration. We go for refuse-derived fuel very less, landfill gas recovery very less. You might have heard Deoghar in the Mumbai, where it's around the year it's burning the methane, as well as nearby Delhi it's Ghazipur at the border of Ghaziabad. There was a land hill of all this waste, and it came down one day, and there were fatal accidents. So we are very good at uncontrolled dumping, which consumes space. It's hazardous for environment as well as health. And this is not going to happen because then there is a VFA accumulation. Accumulation in the sense there is a bacteria which are converting all these volatile fatty acids at a faster rate compared to the methanogenic archaea, which are transforming those acetates into biogas. So there is a lot of volatile fatty acid accumulation, and there is no such transformation at a faster rate compared to the materials or BFAs coming in into the biogas, and then your reactor becomes sour, it becomes acidic, and in that case you might think to feed all your reactors again with the animal manure because it has buffering capacity. And once the pH is quite neutral or from 6.5 to 7.5, then there will be again the anaerobic digestion process will pick up and you will start to have biogas in a good volume. So what are the factors and challenges for anaerobic digestion? Very simple factors, but they do have very decisive role in the name of pH, temperature, carbon-nitrogen ratio, organic loading rate, hydraulic retention time, type of feedstocks, as well as microbial community. We do have challenges in terms of stability of the biogas plant. There is not a single size that fits all, and then it takes a while to start with because it depends what kind of microbial communities are there. And then we also need to create a lot of awareness to our people. To your surprise, and it's very basic information, during 80s, I think every village was having a lot of biogas plant from Government of India, even in today's time also from Ministry of New and Renewable Energy Resources. And in those old times, there was a lot of subsidy. So people got it, constructed in the backyards of their home, thinking they do have a lot of cattle and they can feed all this manure. And after it was constructed, nothing happened and they are still lying non-working because people were not nicely trained. People were never made aware. There was not a single person in the terms of trainer or engineer who can provide help to the farmers or biogas plant owners or aware them what to feed and what not to feed. अपने आप कुछ भी है कूड़ा है हाँ बायोगैस प्लांट में डाल दो गाय का तबीयत खराब है या भैंस का एंड द कैटल्स आर ऑन एंटीबायोटिक and the same cow manure goes to the plant, which is not good because even a picogram or nanogram of those antibiotics coming out in the fecal matter of cattle can kill most of the microbial community present into the biogas plant. और फिर वो किसान एक महीने बाद 15 दिन बाद दौड़ते हुए आता है अरे साहब बायोगैस प्लांट बंद हो गया नहीं चल रहा है because unknowingly he killed all the microbes which were responsible for producing biogas, and then it takes a while to feed it with a new cow manure and start it again. तो ये टाइप का जितना भी awareness है, it has to be created with our all farmers as well as biogas plant owners. Now let's see, there is a case study at MNIT Jaipur itself regarding the food waste. So if you look around, it's a weekly, at the x-axis it's days from Monday to Sunday, and waste generation around, in kilo. And I think in the hostel there are maybe 4,000 to 5,000 plus students, and the rest are, day scholars. And this is only from the hostel, not from the teacher and non-teaching staff's colonies. So MNIT, and look around one big bar on Friday, because it's a weekend and most of the students, they dine outside, go for partying. So we produce around, 500 kilo and around figure per day of food waste only. That includes pre-cooked and leftover food. So, and then it was characterized for approximate and ultimate analysis. And you see, there is a moisture content of around 77%, total solid around 21%, volatile solid 91%, and fixed solid around 8%. And then we do have, characterized the garden waste, green waste, moisture content around 18%, total solid was around 82%, and all that stuff. Then we also got inoculum from one of the biogas plant running on the cow manure in the nearby area. And then we also characterized it for carbon, hydrogen, nitrogen, and oxygen to determine the CN ratio, because if the CN ratio is in the a range of 30 to 35, your plant runs really, really well and produces a lot of biogas. We also went for this elemental analysis of the food waste, garden waste, and as well as the inoculum, where we were surprised. If you could see second from the last, like lead, it was present like 2 mg per 0.2 mg per kg in the food waste. And to us, it was surprising, like from where you are getting lead in the food waste. We went back and checked the things. Then it was discovered then that there is a sauce which is coming out in the form of lead, because most of the time to enhance the color of the tomato sauce, companies mix a lot of lead compound into it. And then there are people जो कि वो समोसे के साथ में सॉस खाते हैं, and then there are people जो सॉस के साथ में समोसा खाते हैं. And if they don't like it, they just simply throw it in the bin. Otherwise, there was no lead in the food material singly tested. Then we also characterized it from Fourier transformed infrared spectroscopy, and then we found there were different peaks which were of our interest, as well as now we tried based on the CN ratio to fix this in the range of 30 to 35, and then we mixed garden waste as well as food waste in different ratios, 85 to 15 ratio, then 15 to 85, 50, 50, all that stuff. We prepared batch bottles, incubated it in orbital shaker, 37 degrees, for 45 days and 90 RPM. And every alternate day, we were checking the biogas production, how much it was produced. Looking over here, look the top green line, it was 75% food waste and 25% garden waste. That was close enough in the CN ratio of 30 to 35, which was the highest. And if you look around only food waste, it's the second line from the bottom, the red one. And if you look around only green waste, garden waste, it's yellow line from the bottom, the first one. So there's a huge synergy once you combine garden waste as well as food waste, because then the CN ratio comes in the range of 30 to 35, and you do have higher production of biogas. And it was around 1.7 times higher compared to the anaerobic digestion of single biomass, either food waste or green waste. But combining or blending food waste as well as garden waste in the ratio of 75 to 25 enhance the biogas production. Increased to 36.5 million in 2015. Then there was a huge increase in 1 billion Indian rupees from 2015 to 2020. Investment in the area of tourism industry, but how much food is wasted, nobody calculated. So for that, I think we designed experiment, we surveyed, and then we came to the point that result I will be discussing. But before going there, if you look around, like Jaipur as a city, as per Jaipur Municipal Corporation, Jaipur city generates 1,200 tons waste per day, and out of that, maybe around 40% is food waste. But how much hotel sector is contributing in those 40%, we don't know. So what we did, we characterized the hotels into 3 groups, like a single star, like number 1, and 2 star and 3 star in the group 2, and 4 and 5 star in the group 3. So there were 29 1 star, 22 3 and 2 star hotels, and 19 4 and 5 star hotels. They were chosen based on their location, where a lot of guests come around at bus station, railway station, airport, tourist records, and then there was a huge questionnaire prepared, and we collected the data like here. If you look around the rightmost column, the segregation is done mostly in 4 and 5 star hotels, and that is around 84%. Although we had really tough time because most of the hotels, they were not ready to share the data. And then 0 and 1 star hotel, they hardly segregate, because 0 और 1 स्टार वाले होटल के पास कौन जाता है, भूखा आदमी, गरीब आदमी, उतना ही लेगा जो वो खा जाएगा, छोड़ने का सवाल ही नहीं उठता. But in 4 and 5 star hotels, there is a lot of lot of people who just go and don't consume the whole food. And if you look around at the waste generated, it's only 5 kilo in the peak season from November to February in the 0 star or 1 star hotel. It's only 12 kilo in 2 and 3 star hotel. It's per day. And then in 4 and 5 star hotel, it's 132 kilo per day. So you can imagine how much food we waste once we start to earn more. Basically, we are burning the currency or the notes what we earn. So that is also a very good message over here. Looking at here, if you see a star hotel category 1, 2, 3, and 4 and 5 star. So there is a huge increase once you start moving from 0 or 1 star to 4 star. And then most of the food is wasted in the dinner. Most of the food. So for that, I think we took the food waste from there. Then we tried to pre-treat the food waste, just hot water pre-treatment, just cook them in the hot water at different temperature, 60 degree, 80 degree, and 100 degrees for 10 and 20 minutes, mince them. It's just to loosen their cell wall so that most of their sugar and polysaccharide materials can be released. But this is all this matrix, how the treatment was done and what was the severity factor and all. And then we also characterized it with the Fourier transform spectroscopy. We also started to know the pH at 0 minutes, 10 minutes, and 20 minutes, of the treatment. And then we also calculated volatile solid release. It was more or less almost same. There is a not significant difference because temperature was not that much high. There was a soluble protein which was coming out after 100 degrees for 20 minutes or 100 degree 10 minutes. It means there were disruption of the cell walls and the proteins which were in the limits, they were coming out into the solution. Then we also measured the COD, chemical oxygen demand. More the COD, more is the chance that it will produce more biogas. Then there was a characterization in terms of scanning electron microscopy to study the surface behavior, what kind of activities are there or what kind of modifications are surface degradation is there or not. So there was a huge, you see in the lower right corner picture, at 100 degrees for 10 minutes, there was a rupture of the cell walls and particles were smaller compared to the untreated and 60 degrees and as well as 80 degrees for 10 minutes treatment. If you look around, it was a severity factor like 2.9 in the sense 100 degrees for 10 minutes. That was the best treatment where you can have cumulative higher biogas production rates compared to all others. And that fellow, he also designed a small this type distillery water bottle type of biogas plant, and he filled that biogas in the Hero Honda motorcycle tube, and it was working quite well. And I think he gifted all this setup to 1-star Garib Wala Chota Sa hotel, and that fellow is very happy now. So this was working quite well. Yes. The conclusions were 4 and 5-star hotels. They are the biggest generator of the food waste. Hot water pretreatment enhanced the biogas production, and the enhancement was around 41% at 100 degrees centigrade for 10 minutes. If you cook the food waste or pretreat, you can increase the biogas production levels. Third case study was from Nagpur city. It's the project called Swachhta Doot. They started this project before 19 years ago. Nagpur used to generate at that time 801 tons per day in the waste, and the population was at that time only 2.4 million people. So this was started with local community, NGO, and public-private partnership model. There were people who were trained scientifically and hygienic process. The Swachhta Doots, it generated around 2,000 employment and one दूध covers 200 to 300 homes. स्वच्छता दूध in हिंदी इसका मीनिंग कभी कभी गड़बड़ हो जाता है, तो in English you can call it cleanliness messenger, otherwise दूध को लोग राक्षस का रूप में सोचते हैं. So awareness, स्वच्छता मित्र, who was the mediator in between the homes and स्वच्छता दूध. And then there was 100% door-to-door collection. It was segregation, nicely designed three-tire, cycle rickshaw, so that it can easily be taken into the streets of Nagpur. And most of the, solid waste could be collected in different bins, which are organic and glass, plastic, metals, etc. What kind of benefits were there? There was an improvement in social standard and financial stability of Swachhta Doot. They started to earn something. Awareness of consequences of unscientific waste is spreading, because then finally the waste you throw, it will one fine day, it will come and bite you in the form of dengue, in the form of malaria, in the form of diarrhea, anything. So we have to be very careful that what we are throwing and where we are throwing. And then by this project, there were belongingness developed in the society, that this is हमारा मोहल्ला, हम इसको साफ रखें, like that. So economic savings बहुत सारी हुई, around 50 million Indian rupees per year. New avenues for employment. There was a composting of organic material developed from all this organic waste, recycling, and then landfill sites, they become free, because then there was less and less landfill. Then there was an improvement in public health and life quality. I'm not going to talk about this because the time is not allowing me. So there was a case study where I worked for the food waste and biogas production in the Oslo. So I'm very happy to share that the technology on which I was working, it has already been into the practice, and now there are n number of buses which are flying, around 87 city buses which are flying on the biomethane generated from food waste of the Oslo municipality. And it's fantastic, with the 13% reduced CO2 emission, and then there is a decline in nitrogen oxides as well as soot particles. And the bioresidues, it can be used as biocakes in the organic farming. So take home message for all of us, like there are opportunities in the terms of innovative and sustainable technologies. What we need to develop is energy transition, its access and security for upcoming future, where there is an abundant availability of biomass in a country like India, and advanced technical potential for bioenergy production has to be developed. There is a still untapped export potential in country exists. This is less expensive land and labor in developed countries, in our own country are much more cheaper compared to the developing countries. There is an intercontinental trade in EU and Asia for ethanol, wood chips, and pellets. What challenges we are facing, where we have to focus more and more so that we could take maximum benefit from the existing opportunities. Like in the terms of technical challenges, there is a difference in properties of biomass depending on variety, type, and origin of the same, which can be less suitable for direct use, such as co-firing at thermal power plants like bagasse or ganne ki khoi, thermal power plants mein koile ke saath mein. Plus, there is not a single size which fits all, that a waste treatment process may work well in the Jammu and Kashmir, but that may not work in the state of Tamil Nadu well, because of the climatic and geographical differences, as well as the difference in the biomass types. Economic is still expensive than fossil fuels. जिस दिन बायोथेनॉल पेट्रोल से सस्ता हो जाएगा, हम लोग बहुत चालाक लोग हैं, देसी लोग, है ना, वो every day on a single fine day it will be available anywhere. The day it becomes cheaper than petrol. Logistical, bulky nature है biomass का, it has to be compressed, and lack of technology makes it difficult to pack the biomass in a compact form for cost effective transport. आपने देखा होगा भूसे को ट्रैक्टर ट्रालियों में बहुत ज्यादा लोड करके, और ट्राली के बाहर से वो भूसा गिरते रहता है, So those technologies to make it compact, we still lack, and if we do have, it's very expensive. So we do have to look for that we can form it its pellet as well as the briquetting so that it can be transported more easily. There are barriers at an international level in the form of import formalities, contamination risk, quarantine. That's a picky word nowadays. Ecological, there is a lot of biodiversity and nutrient depletion while transportation, as well as there are social issues in the form of child labor and occupational health. So we all have to take care of all these points before we try to get maximum from the opportunity in the area of bioenergy in our country. So I would like to thank all my international and national collaborators, my students, acknowledgements to all the funding agencies, and thank you very much for providing me opportunity to share the things with you. And let's change by exchange. Thank you so much. If there are questions, I would like to welcome them.
Thank you very much, Dr. Vivek. Can you hear me?
Yes, sir, please.
Oh, thank you very much. It was an excellent talk on circular economy, a lot of case studies, and it was very interesting. And I think we will open up the floor for questions. Audience, we would request if you have any questions, please ask Dr. Vivek.
Good morning, Vivek sir. We have questions from our audience. The first question we have: how waste sector is affected during pre and post COVID lockdown?
Okay, thank you. Very timely question. And the thing is, especially if we talk about biomedical waste as well as non-biomedical waste. There has been huge impact on the waste collecting people, on their lives, as well as the waste generating people like we. And if you talk about biomedical waste, before COVID and after COVID. Before COVID, most of the biomedical waste at the hospitals, they are provided with yellow bins, black bins, and blue bins to collect the incinerated waste or all those. Yeah, I think most of you know those details. And it goes directly for incineration. But as soon as the COVID arrived, and I'm just focusing only on biomedical waste, not as a whole on municipal solid waste. But as soon as the COVID arrived, then there was a biomedical waste which started to increase in the amount without any formal regulation. And that was mostly the PPE kits, that was mostly the gloves, that was mostly the masks, that was mostly the sanitizer bottles or any material in which the sanitizer material was there, as well as this sanitizing tunnels as well as the sanitizing equipments, because if they are broken, they are repaired, and even after repairing all these machines, if still they don't work, it's just wasted. So there was an increase in this non-formalized biomedical waste, which came along like with the household waste. I mean, in terms of MSW also. And then there was so much scare in the waste collecting people. Even they didn't, go out, and even if they got out, people welcomed them with garland. People gave them extra money. People gave them a lot of cloths and things to, protect themselves. But still, there was, hue and cry in normal public that अरे बाबा मैं कैसे फेंकूं इसको, मैं कूड़ा दे के कैसे आऊं, ऐसा ना हो कि ये गीस घर से लेकर के आ रहा है और मुझे भी कोरोना ना हो जाए. So that kind of mental, impact was there. But there has been chances where people who were aware, they started to burn at least the mask in the close proximity of their own muhalla, or in there. I have seen people at friends' place or nearby where were people जिन्होंने मास्क को चिमटे से पकड़ा और गैस पे ही जला दिया और फिर बोले कि नहीं साहब ये तो कूड़े में नहीं देंगे, हमको हुआ है नहीं हुआ मेरी वजह से किसी और को ना हो जाए. So I think in waste management practices, it could be medical or non-medical. In a country like India, we have to feel responsible कि अगर मैं गंदा कर रहा हूं तो मैं अपने लिए ही कर रहा हूं, आज नहीं तो कल ये घूम के आएगा. जी.
Thank you, sir. That makes a deep sense. Next question we have: What are the
Yes, please.
alternatives of algal biomass with respect to biofuels? What are the alternatives?
Alternative of algal, exactly क्या पूछना चाह रहे हैं बच्चा जो है?
Uh, Actually, I think he is or she is asking about the rather than algal biomass, from what
अच्छा,
type of other biomasses we can generate biofuels.
हाँ, ठीक है, ठीक है। तो एक तो है एल्गल बायोमास के तरफ से बहुत सारा लिपिड है और उस लिपिड के थ्रू आप बायोडीजल बना सकते हैं। प्लस वो उसके वाटर को लेकर के हम बायो रिमिडिएशन कर सकते हैं, वेयर देयर आर लॉट ऑफ न्यूट्रिएंट्स गेट एब्जॉर्ब्ड एज वेल एज एब्जॉर्ब। दो चीज है, और एल्गल ग्रोथ काफी अच्छा होगा बिकॉज देन देयर विल बी लॉट ऑफ ऑर्गेनिक मटेरियल्स। तो अदर देन दैट, इफ वी वांट टू ग्रो सम बायोमास or enhance this biomass, there has been practices and it was rather more on literal side कि हम CO2 पंप करते हैं इंडस्ट्रीज की तरफ से, जो प्रोड्यूसर गैस आती है उसकी चिमनी का CO2 हम एनवायरमेंट में रिलीज नहीं होने देते, उस CO2 को हम पंप करते हैं एंड देन देयर इज अ मोर ग्रोथ on the algal side, which gives more lipid, then that lipid could be transformed into biodiesel. Other than that, there is a lot of edible oil produced in a country like India from industries which is useless. जैसे मैं आपको लेज चिप्स है, जैसे आलू चिप्स या लेज का कोई भी चिप्स है, तो बहुत सारा मेरे ख्याल से आई डोंट नो हाउ मेनी साइकिल्स, उतना बार चिप्स बनाने के बाद में वो तेल खराब हो जाता है और वो अगर हम आप अगर खाएंगे तो वो खाने में अच्छा ना, वो टेस्ट नहीं आएगा चिप्स का। एंड फॉर दैट दे यूज और दे अबंडन दैट ऑयल, वो तेल को छोड़ देते हैं और वो अब यूजलेस हो जाता है। So all these edible oil which has really been utilized for their potential, all those animal fats from the slaughterhouse, etc., this could be and are rather good source of biodiesel, because then we go for reaction of transesterification. We make sodium hydroxide or potassium hydroxide. We go at higher temperature, maybe 100 plus or 60 degrees, and then there is a reaction called transesterification, where there is a transfer of ester groups, because they all are fatty acids, especially oil and animal fat, and then we get glycerol as well as the biodiesel. So biodiesel, it has good property compared to the others, not other rather fossil diesel. It has less emissions compared to the fossil diesel, and the glycerol which is produced as a byproduct in this transesterification reaction, that can be utilized by the pharma and cosmetic industries to make other products. So that is one way. Plus, there has been initiatives for synthetic photosynthesis, or organic solar cells, but so far there has not been big breakthroughs into that. Yes.
Thank you, sir, for your answer. Next question we have that any genetically study is available for biofuel, means genes which are related or helpful to study biofuel formation in a cell, which type of gene is contributing into formation of biofuels?
Okay, so what I would like to suggest here, biofuel itself is an end product. It comes from some other living source, like कोई biomass है, क्योंकि biofuel को कोई particular gene directly नहीं बना रहा. There are chemicals, there are biomass where the particular organism having genes works, and then the biofuel is produced. Suppose, let us take example of lignocellulosic biomass, like पेड़ है कोई, तो लिग्निन क्या करता है, सारे सेलुलोज फाइबर्स को चिपका करके रखता है, इट वर्क्स एज ए नेचर्स ग्लू। घास में लिग्निन का अमाउंट कम होता है इसलिए वो सॉफ्ट होती है, लेकिन पेड़ है, नीम का है, आम का है, बबूल का, इसमें लिग्निन का अमाउंट ज्यादा होता है। खास करके आप हिली रीजन्स के पेड़ को देखेंगे तो बहुत लंबे होते हैं और बहुत स्ट्रांग होते हैं, बिकॉज दे आर कॉल्ड सॉफ्टवुड, नॉट बिकॉज दे आर सॉफ्ट, देयर आर अनदर रीजन्स, बट उनका लिग्निन अलग क्वालिटी का होता है कंपेयर टू आम का पेड़ का लिग्निन। अब उसमें क्या है कि एक जीन होता है पाल जीन, फेनिल अमोनिया लाइएज जीन, तो अगर हम उसको साइलेंस करते हैं तो लिग्निन का जो, क्योंकि लिग्निन इटसेल्फ इज अ पॉलीमर एंड इट हैज बीन मेड फ्रॉम एन नंबर ऑफ एरोमेटिक एंड मिक्सचर ऑफ एलिफेटिक मोनोमर्स, तो अगर हम लिग्निन सिंथेसिस को रोकते हैं So there has been experiments in the Arabidopsis thaliana, which is a model plant, कि हम low lignin plant produce करें और directly उसको हम biofuel production के लिए भेज दें. But so far it has not been a commercial success. But what this PAL gene performs, phenylammonia lyase genes, that it stops or interrupts the enzymes which are required to synthesize the monomers of the lignin, and then lignin is less synthesized, and then the plant don't develop a lot of lignin, but it develops only lignin from other sources which are really, really important to survive, because lignin also protects the plant from different pathogen attacks, and it gives strength and rigidity. It's also water repellent, etc. So for those things it survives. Otherwise, if somebody wants to produce a lignin less plants, it's impossible, but there will be a little lignin which is really, really important. So somebody can play around with phenylammonia lyase genes or other lignin synthesis genes which are involved in the lignin synthesis pathways. Yes.
Thank you so much, sir. There are more questions, but we have less time. We will take it further. Over to you, Dr. Prabhu.
Sure.
Oh. So Dr. Vivek, I think shortage of time, I think we are just skipping off the question and answers. And I think we can just if there are more queries regarding from the audience, so that they can get with that anything. So once again, on behalf of the organizers and all AKS University and Department of Biotechnology, we thank you for your valuable time and the lectures.
Thank you, sir. Thank you all. Thank you.
Dr. Pawan, good morning.
Good morning, sir.
Professor Kamlesh, good morning.
Sir, good morning, sir. How are you, sir?
Namaste, sir. Good morning, sir.
Vivekanand Saab, good morning. I am fine.
Sir, good morning, sir. Namaste, sir.
So that eminent speakers can join here to be in this particular event, sir. Thank you, sir.
Thank you, Dr. Tiwari. So, Kamlesh, should we go ahead with my talk?
Yeah, definitely, sir. And I will introduce you firstly, sir. So
okay.
Let me introduce. Yeah. Sorry, sir. Actually, I missed that document. Arpit, may I request you to introduce Pawan Juthur sir on behalf of our organizing team? Arpit?
Sure, sir.
Yeah, please.
So for the session of Biofuels, the future of moving world, that is our session 4 of e-refresher course in biotech for 14th and 15th September. The convener of this program was Dr. Pawan Juthur sir. He is a group leader of Omics of Algae Integrative Biological Group, International Center for Genetic Engineering and Biotechnology, New Delhi. His research interest is on microalgae that holds promising source of renewable energy to replace diminishing oil reserves as a source of lipids for biofuels. Algal oils are rich in triglycerols, and that serves as a material for conversion to biofuels. So his studies on the biosynthetic pathways and rate-limiting steps as a triglycerol formations in microalgae are still in infancy. His research team aims to study the overall regulatory genes in tag biosynthesis and catabolism pathways, oil mobilization, and also RNAi-mediated silencing altering the lipid content to increase in overall lipid productions. In this way, Dr. Pawan Juthur sir is working efficiently and effectively with high number of research papers at the International Center for Genetic Engineering and Biotechnology. So we welcome you, sir, again. Thank you so much.
Thank you,
Thank you.
Arpit, and thank you for your
Welcome.
time.
So, thank you.
So, hope you are able to see my slides.
Yes, sir. Yeah, yes, sir. It's here.
Okay. I'm not able to see the slides on my presentation. So here. Okay. Yeah. Hope the slides are visible. So, uh,
Yes, yes, sir.
today I'm going to discuss, yes. So today I'm going to discuss on algal cell factories, the fourth generation perspective for industrial biofuels. So before starting my talk, I would like to give a glance of what ICGB and where we are working upon. So ICGB is an international organization which works on promoting research in basic sciences and life sciences and biotechnology, and it provides training and promotes sustainable global development globally. And we have three different places situated. Our headquarters is in Italy. I'm currently working in India, this middle one, and we have one more campus in South Africa. These three are the main three components of ICGB located at different places. And we are especially involved in activities that are promote scientific learning and innovation, helping the member state countries so which can achieve sustainable goal development. So the major areas are agriculture, nutrition, health, food security, and industrial development. So if you see, we work on different macro areas of research like infectious diseases, non-communicable diseases, medical biotechnology, industrial biotechnology, plant biology, and biotechnology. So throughout the three components, or what we call as three host countries, we are under different micro areas of research. I am presently working on industrial biotechnology, where we try to work on algal biofuels, and my specialization is in omics of algae. So we try to understand the basic biology of the microalgae when subjected to different conditions, especially not only for production of biofuels. We are trying to understand how the biomass can be enhanced, biofuels, and the byproducts. So I'll be putting at a glance of what we do at our lab in later slides. And as I said, we are a cutting edge research institute with three laboratories located in Trieste, Delhi, and Cape Town. And there are 66 member states which are present throughout the world who are the members, and we try to train them in terms of science and technology, and also they get postdoctoral, doctoral fellowships. All these people of the member countries are eligible to apply for these things. Along with that, we have different programs like meetings and courses, where ICGB conducts meetings and courses throughout the world, and it is open for everybody throughout India and the world. And many eminent and give their expertise talks in these fields. And every year we have different fields like human health or plant biology and industrial biotechnology. Likewise, for international scientists who are interested, they are the international research grants. And if you are Indian, you can apply for the research grant with other components of ICGB, where your collaboration suits you. So that the ICGB, and it's a very competitive research grant, and ICGB gives a very good amount for the kinds of research. So it's called the collaborative research program. So these are the highlights what we do at ICGB, one of few highlights of what we do. And if we go to now into the brief. So today my talk will be mainly concentrating on these aspects. So what are kinds of biofuel generations? Our experts were talking about what kind of different generations are there, what is kind of what we call as biofuel generation. I'll be explaining in the next slide. Why we need the production of biofuels and classification of algae. Why algae? So why only algae is required? or one of the major feedstock for production of biofuels. So, and the paradigms in algal biotechnology. So, what can you do to understand the basic nature of the algae so that you can able to produce your desired product or a biofuel or a high value product or a biomass. So, through an omics of algae is an amicable solution to understand such systems so that we can produce the desired product of our interest. And finally, I will be talking about fourth generation biofuels because this is the where the near future will be there in terms of algal biofuels or any kind of biofuels where you can genetically modify the organism to produce a product of your desired interest at industrial scale. So that's called fourth generation biofuels. And finally, so there is always a question like yesterday also one of the attendees or participants were asking, is the biofuel sustainable? Yeah, why can't it be? So there is a roadmap which was published recently in 2017-18 by a group of uh, 20 institutes where they shown that there is algal biofuels are feasible and they can produce a gallon at $7.50 per gallon of that at that price. So they are still this is a roadmap that the algal can be, and I'll give a glance how what it is in my last slide. So to start with that, we would like to start with this figure where the estimate of developed countries by 2030 will be 57%, where from 93.2 million barrels per day, we may require around 106 million barrels per day. So there is a lot of requirement in terms of biofuels. And now presently in 2010 or 2006, it's only 1% near. So by 2030, the estimate is around 5%. So the increasing demand of biofuels and other products is very much required, and there is a need to really look for the alternative sources for the fossil fuels, especially for the biofuels. So in this context, I'll be discussing about what are the biofuel generations, what we call as first generation, second generation, and third and fourth generation. Yesterday, Dr. Reena was also emphasizing on first, second, and third generation biofuels. If you see this diagrammatic representation, there's a raw material section, technology of transformation section, and products of selection. So these are how we need different raw materials, and that has to be translated to a technology process that so that you can produce bioenergy, biofuels, biochemicals of your interest. So what are the things which are required here? We have to understand. So there are few first generation biofuels. I will just take a couple of seconds in explaining this slide because this is very important, especially for the students to understand if they were interested in biofuel research. Okay, so first generation biofuels are especially from edible crops like sugarcane, rice, wheat, potato, sugar beet, etc. So, but the major contradictory to the first generation biofuels is you cannot utilize the food resources because it's always a debate that you cannot compromise on food resources, and because this is a very important area to generate fuel. So that's where second generation biofuel has came into existence, where you can use in second generation biofuels, especially lignocellulosic biomass like sugarcane ballast, forest residues, cell biomass for fermentation, grasses. जैसा घास होता है तो you have different kinds of grasses that can be used as a lignocellulosic biomass. So that is what we can use to convert into bioethanol or whatever biofuel molecule you want. The third generation is especially the microalgae. So microalgae again like Bacterococcus or Cryptoconium, a lot of microalgae is present where you can use that microalgae to capture through different sources like sunlight. It requires nutrient and the water sources where you can grow the microalgae to produce biofuel of interest. And especially from third generation biofuels, you can produce biodiesel, right? So likewise, you have other products also which can be produced from algae. I'll be discussing in a few seconds. And the fourth generation is non-edible, especially what we call it as the genetically engineered algae or anything which can be done. And mainly it can sequester your carbon dioxide. You can use the forest waste which can be used to convert into biofuel. So that's why mainly the fourth generation is a genetically modified feedstocks which can be used for production of biofuels. So that's how first generation, second generation. So today my talk will be based on third generation biofuels, but not on translational side, but on basic research side to understand how the third generation biofuels mainly work upon. Uh, when coming to the technology transfer, there are different kinds of technology transfer because once you have a feedstock, you have to convert that feedstock by using different technology aspects. So it may be physical like ultrasound, mechanical extraction, thermochemical, pyrolysis, gasification, combustion, or it may be a chemical like hydrolysis, solvent extraction, and super extraction. So using different approaches, you convert your lignocellulosic or any kind of biomass into by product selection where different products can be generated in form of bioenergy, biofuels, or biomaterials. So this is how different biogenerations and each sector is being developed in their own niche so that you can produce at a continuous scale in the future. So there are developments which is happening, and it's a very interesting paper which has come up in 2017 review. If anybody is interested, you can just follow this reference link and you can get more information on that. So as I said, why do we need biofuels? So fossil fuels are limited. We know that by 2050 we will be deficit in fossil fuels and they are always diminishing. So we should have an alternative source of biofuels which can be non-environmental pollutants. So global energy demands keep on increasing. So it's always increases and there is a way how you can do that. And also CO2 released from the fossil fuel causes climate change. So how can you mitigate this CO2 so that you can use that CO2 to form important biochemicals? Last but not least, liquid petroleum transportation fuels are very hard to replace by any other renewable sources like wind, solar, and hydro. There are different, as I said, that there are different kinds of renewable sources, but if you want liquid petroleum transportation, which is especially biodiesel, bioethanol, all these things, jet fuel and all, that has to be replaced with fossil fuels with with understandable like lignocellulosic or algal biofuels. And especially algal biofuels are carbon neutral. So that's the main thing why we need biofuels in Sinai. So basically, you can produce lots of different varieties of compounds from these, and there is a wide variety of classification of algae. And I think we read about algae from class 8, but we try to neglect it as a small microscopic, and especially we don't even enter the ponds because of the scam present in that. So because of the green dirty material, we don't touch it, but that is called a gold mine, green gold mine. People call it as a green gold mine. So if you try to work on that, that's what that's make us fascinating. Why we should work with these such kind of organisms. There are three types of algae, which is a cyanobacteria. Different types of cyanobacteria are shown in this figure, where you can see that there are a wide variety of cyanobacteria, and this is a microalgae where our groups mainly works upon. These are different kinds of microalgae and different shapes of microalgae where we are producing different kinds of byproducts. And this is a macroalgae. Macroalgae is again very important source of different production, and there are wide varieties of macroalgae which are useful for the generation. So mainly to understand, especially for students, there are different kinds of macroalgae, and depends on what kind of product you are interested in, you can work upon those things. And especially algal farming is one of the main important upcoming field where you, just like agriculture farming, you can do algal farming to produce lot of products just for nutraceuticals, pharmaceuticals, fish feed, biofuels, or anything of these things. So that depends on what kind of feedstock you select for these things. So even for wastewater, so this is one of the best source. Like you can treat your wastewater to make it a potable water or a salt water into a normal water. So there are a lot of applications which has to be worked out, and this will be as I said, the gold treasure of future, where people are working on it to understand different aspects of this. So why algae? I already told, algae biomass derived from biofuels promises great advantage because the productivity per acre. So algae can produce higher amounts of oil for any land plant or land crops than any of these things. That's the reason why it's the greatest advantage, and it can grow in any types of any types of water varieties. So especially marine waters, estuary waters, even it can grow in wastewaters, and it can be grown in non-arable land. So it thus you can always be safe with the food versus fuel problem, and especially it can mitigate the greenhouse gas emissions. And potentially, the best way why algae has a greater potential is they at any means of time they can produce biofuels along with other high-value products which are important for pharmaceutical, nutraceutical, or any kind of industries which we are making of. Especially algal byproducts or co-products are very important nutrient pharmaceutical approaches. Even, for example, my favorite example is omega, which DHA, which we usually our children drink in Bonvita. The DHA which is supplemented in the Bonvita is from algal DHA. So it's absolutely, even the fish what we eat, the omega-3 fatty acids which are present in the fish are mainly from this food they eat, that is especially microalgae or macroalgae, which is microalgae present in that. That's why they are the results for omega-3 fatty acids. That's omega-3 fatty acids or such kind of nutraceutical products are very, very relevant in microalgae. That's why at any way, any point of view, algae are beneficial in like producing biofuels or co-products along with the biomass. So even the biomass can be used as a fertilizer. So there are X number of advantages of using that. This is a very simple schematic and a very popular schematic of making biofuel from algae. So I will just explain in brief what exactly it is. So here you have different sources. It's an algal pond where you grow it. It's a photobioreactor or the open pond where you can grow the algae. And especially for the algae, you need nutrients, water, and the CO2. So, and along with the sunlight. So these four components are the main ones which are required, and you can grow the algae, and the algae should be settled and separated from the water because the algal biomass is required for the extraction of the lipid. So you can do it, you can do it either through flocculation, that is settling the algae, or through dissolved air flotation where you can bubble the float, make the algae float. And some of the algae are naturally flocculent, so they can settle, they can come up on the top so that you can just sieve it and separate it from water. Or you can centrifuge it. Once you have an algal biomass, you can see it here, there's the algal biomass. Once you put in that, put the solvents and try to extract. The terminology is called transesterification, where you can produce a biofuel, and there are different kinds of processes where you can treat it and you can produce a raw oil or a hydrogen, biohydrogen, or a jet fuels of different products of our interest. The interesting thing is it's a circular economy kind of phenomena where the unspent can be used as a sludge for fertilizer, and the energy biogas is produced for turbines to generate the power, and you can recycle the nutrients or water to into the algal growth chambers again back and just add supplemented but and it can go. So water is also not getting wasted, and they can recycle the nutrients in such a way that it's a circular phenomena where you can use the raw materials back and you can produce it. So it's an overall conceptual way how to produce a biofuel from microalgae, and it's a very, very popular review which has been published by Pinikos et al. So having known all these things, are we at a stage that it is feasible? No. At this point, algal biofuels are at a very higher cost at what we are expecting. So large scale production is at a developmental stage, and there are main things where the basic challenges are large scale production and harvesting. Other than that, if you try to improvise on these different parameters, I will not go through details of all these things because there are a lot of individual parameters which has to be discussed on this so that each thing can be worked upon. So yesterday, Dr. Reena was talking about photosynthetic sunlight activity. So photosynthetic active power radiation is a very important phenomena where you have to supply with adequate sunlight so that it can actively grow upon. So these are the very, very important conditions at large scale production, and people are doing it. And in India, very few companies are doing it at a large scale, especially very popular company Reliance has a huge plans in Bhavnagar where they are trying to develop the continuous production of large scale production of algae, and they have been I've seen in a lot of their talks that they have been successful in growing the algae for 1 year continuously and producing the biofuel. So thus there are different parameters at an industrial scale where we have to, because we are talking about a very high scale. So large scale production, there are other parameters which has to be set, and especially the cost is harvesting. So you can decrease the population, filtration, centrifugation, drying. All this leads to the reducing in cost. So now, because of the high cost, it is not feasible. But if you work on all these things, how the other teams in US have worked on to bring down the cost is an example of last my roadmap where I'll show that. But at present, we need a lot of challenges to be addressed. So this is a small video which before starting my lecture, I want to show you guys, and it's a very important, very interesting video which is developed by ExxonMobil about the algal, and a very beautiful video. So I like this. So just 1 minute. So actually I always show this 1 minute clip because it boosts the energy of algal biologists, and as they said, it is an unidentified treasure of energy. So basically, it shows everything what was explaining, and we call this as B3 algae, our thematic in the lab. So because we need B3 kind of a different ingredients to grow the algae. Or just if you see a computer needs an process input and it gives an output, and the data is processed in the computer, right? So just like that, in algae, it requires some input. Input sources are sunlight, sunlight, carbon dioxide, and water, which are the very main important sources to an algae. And the algae takes up it, process these three forms, and generates you multiple products. That's why we call it as B3, where B3 stands for biomass, biofuels, and high value products or biorenewables. So in this way, you can produce biomass, biofuels, high value products, hydrogen gas. Yesterday, Dr. Venkat Mohan was talking about hydrogen gas, which is used for fuel cells. Even you can generate electricity using algal this thing, and hydrocarbons, which are plastics, bioplastics, and other petroleum chemical substitutes. Likewise, you have different products which you can generate from these algae. So coming to the paradigms in algal biotechnology, basically today I will be talking about one important parameter what everybody throughout the world works upon. So when you try to and we want to enhance the biofuels or lipids in the biofuels are nothing but the lipids, triacylglycerols, which are being accumulated in algae. So when you want to increase the lipids, you have to do some conditions, right? So either you do the genetic engineering, you try to transfer a foreign gene so that it will be overexpressed and you can produce a lipid, or you can apply a nutrient deprivation condition where so your lipid can go increase and your biomass. So in most of these conditions, what happens is your lipid increases, but your biomass gets compromised. So there is another kind of strategy, what we call is a media engineering or a chemical modulator strategy, where you can enhance both lipid and biomass, okay, against the stoichiometry, but you can generate such a condition that your biomass is not getting compromised, but you can enhance your lipid content. To understand that, you need these tools to understand the physiology of the. We are not doing any new, but we have to understand the environmental growth conditions of the algae. So, to understand that, we need these tools like omics research, pathway engineering, genome editing, synthetic biology, so that you can put all these things together to develop into a microalgal cell factory where you can engineer or modulate such a substance to enhance your lipid or a high value product, so and finally produce without compromising the biomass. So that's what we call it as a paradigm in our algal biotechnology, where you can you have a condition to either increase to keep your biomass constant, and you can increase this. So there are different factors that can influence those things. So here, understanding the cellular dynamics of microalgal cells under nitrogen stress using multi-omics platform to identify enzymes and coding and evaluate the oil accumulation mechanisms in native oleaginous microalgae contribute towards engineering the regulatory pathways for increased oil production. So what we are showing today, a case study, what we are doing in the lab, and it's an indigenous microalgae called Parachlorella kessleri. You can follow our publications also recently published in Biotechnology for Biofuels and other journals, where we try to work on indigenous marine microalgae to understand the oleaginous nature, because that microalgae is capable of producing up to 50 to 60% of lipid, and it is subject to nitrogen depletion. So I try to put an emphasis that what is we exactly looking for. So the stress biology in microalgae is very important to understand the phenomena of basic biology, what is happening. So basically, when you see certain things, they are especially two conditions. Nitrogen replete means you have all the nitrogen nutrients supplied to that, and the algae is growing completely normal. So when you try to remove one source like nitrogen, phosphorus, or sulfur, the main components or major constituents from this component, you will see that the lipid synthesis goes up, especially in form of triacylglycerols. In the middle, you can see that my algal green cell is converted to yellow cell, and when you do a fluorescence microscopy, all your cells look yellowish orange color, which is nothing but lipid bodies, and that is called neutral lipids or triacylglycerols. Triacylglycerols are the storage lipids of any algal cell. So when the triacylglycerols increases, that is what the biofuel precursors, what we are looking for, especially the photosynthesis and beta oxidation, which are the important aspects of microalgae, goes down. So we want to understand what are the genes which are involved in that, and some of our audience were asking how do we look for the genes, and also the omics study is the one which is responsible to understand what kind of genes are upregulating, downregulating, so that you can finally understand those concepts and you can show that what can be the best way to do it. So when the beauty of this microalgae is you can get back the normal conditions. So when it is in stress condition, it accumulates the lipid. You take these microalgal cells and put it in the complete nutrition media. Back within 24 hours, the microalgal cell can become a normal cell. That means the photosynthesis, beta oxidation, all these central metabolic pathways can come up and they can produce, they can show the activities the best of it. They'll be normalized, and your tags can be recycled into precursor molecules and membrane lipids, and that's how you can recycle. So if you can understand the phenomena to generate the oil, that is triacylglycerol precursors within the cell, and the algal cell can pump out or milk the oil outside the cells, and that can be taken back, because the cells should be replenished. If they are not normal and they are not healthy, you cannot produce continuously oil. So there should be a biological mechanism how you can maintain these cells in a normal way and recycle back into deplete media and replete media. In that way, you have a continuous culture that can be used up for the production of biofuels. This can be a very good discovery if some breakthrough comes up how to do up these replete to deplete cycles so that you can produce the biofuel of interest in a continuous phenomenon. So such kind of challenges are being looked in our lab. So, as I said, we try to look upon in parachloral cassellary. It's a marine isolate, and we have done a different kind of starvation. So it's a glance of what we have done it. So it you can see the first left-hand side. This is the biomass, and the green says it's a control, and the blue one says that it is we remove the phosphorus condition. You can see the insert. The control is very green, N minus is a pale green or not a green at all, S minus is a pale green, and P minus doesn't. It almost resembles in like control, but not in a darker way. So there is no effect of growth in P minus condition, but N minus and S minus are severely hampered. The reason is N minus or S minus is sent directly, sulfur and nitrogen are directly involved with the cell machinery. That's the reason we see the arrest of the cell cycle. So we try to understand what happens within cells, and you can see in the TLC plate onto the right side top corner, where you can see the lipid or a tag increases steadily from day 2 in nitrogen once the nitrogen is removed, and by the end of 10th day, the cell is full of oil. So that is how the biofuel precursor is produced, but we want to understand what will be the productivity per cell or productivity per liter per day, and we have seen that because there is a huge compromise of biomass, the productivity enhances in terms of oil, but the biomass is compromised. But in phosphorus condition, because the biomass is not compromised, the oil productivity is compromised. Stoichiometrically, the carbon can be diverted towards either towards lipid or a biomass. That's where a thin line of parameter has to be checked, where you can check whether your biomass is not constant, but steadily you are producing the same productivity. So here on to my extreme right bottom, you can see different kinds of SFA. It's called saturated fatty acids, MOFAs and PUFAs. This is a very important ratio when you want to directly use such kind of tag precursors for biodiesel production. So the ratio of PUFA should be very low, and MOFA and SAFA should be higher. So in N minus condition, you have a more of SFA and MOFAs. So we prefer that kind of precursors for the production of biodiesel. Whereas in the phosphorus condition, the PUFAs are higher side. That means that PUFAs are membrane lipids which are more accumulated because there is a constant growth in that. In that way, so if you want to understand for the biomass, phosphorus condition does not have any influence, but you can produce more lipids. But in case of this thing, but now technology where you can directly take the algal biomass, do the hydrothermal liquefaction or these things, so you get a crude extract from there, refinement can be done and you can do. So now it is not very important at the industrial perspective that you should have this much MOFA and PUFA content. For this, any kind of algal oil can be algal strain can grow for the oil content which is more than 25% or 30% of its dry weight. Take that and do a hydrothermal liquefaction, and you will get the oil of your interest, crude oil that can be fractionated later. So how do we understand this phenomena? So we apply a tool called omics, and omics is a tool to understand the inner depth knowledge of genome, transcriptome, protein, and metabolome, so that it gives a conclusive decision that what kind of phenomena is going within a cell to generate the molecule of our interest. And especially this, the beautiful example is from NASA, where they are trying to understand the astronauts' omics, so that if they go into the space, what kind of nutrition they need, what kind of metabolism happens in them. All these studies are being understood through omics approach, such that they can have the right nutrition and the right kind of metabolism through when they are in outer space. So omics study at a multi-dimensional level is happening for NASA astronauts, where they can understand what will happen to the physiology of the cell when they are in space and all those things. So this will actually understand what is happening. So this is at a higher eukaryotic level, So what we are trying to do is we were trying to understand, explore through omics technology different approaches like using genomics, transcriptomics, proteomics, epigenomics, metabolomics, and microbiolomics to understand different kinds of, and it's a collective characterization of quantification of pools of biological molecules that can translate the structural functional dynamics of an organism such that you can understand what is happening within the cell. So I will take a couple of minutes in explaining this slide because this is the where it is very important to understand the multi-omic phenomena, why we are selecting the iomics or integrated omics or multi-omics to understand the overall cell physiology, because you can see that there are different layers of omics, genomics, transcriptomics, proteomics, fluxomics, and metabolomics. So it's called, when you go from genomics to metabolomics, it's called forward omics. When you do from understanding, you don't know anything about the genome nature, you start with the metabolomics and go ahead and try to connect with the genomics, that is called reverse omics. This is just like reverse and forward genetics. What we try to study, if you have some basic information, you go from the gene level and try to understand what is happening to the molecular or metabolite level. If you don't have anything, you go for reverse genetics approach, where you know about the molecules or what is happening within the cell. You take those molecules and go for the genes, what are upregulating and downregulating. So forward and reverse genetics, just like that, you have a forward and reverse omics which can be integrated, and especially the crosstalk between these things are very important. Any single omics will give an information of what is happening, but that does not really translate what is happening to the end, because the example is when there are different there are too many number of transcripts which are upregulating during transcriptome, but that is not translated into a protein when it is coming to the proteomics. That's why it is very important from the transcriptomic what is getting translated into a protein, from the protein what is happening to the metabolite. So thus crosstalk, what is happening can be answered only through multi-omic approach, and that's why it is very important to go through different layers of multi-omics to understand the outcome, what will be the happening with that. So this is how an omics evolution has happened, and that is what the future of single cell omics, where you can apply all these multi-omic technologies to understand what is happening within the single cell. So if you can try to replicate a single cell, what is happening, then you can understand what will happen with the higher eukaryotic system. So that's why the multi-omics in a single cell analysis will be the future of science. So for the omics experiment, you should have suitable number of biological samples, technical or analytical or biological variation. These are very important parameters which are when you're doing an omics experiment, everybody should have a consideration of that. So I'll not give into the depth of this. I'll just directly go. So today I'm going to discuss about reverse omics approach, where we start with metabolomics. Metabolomics, we have targeted metabolomics and non-targeted metabolomics, where targeted metabolomics, you know the molecule of your interest, you take that as a standard and you try to look what is happening within the cell. That is called targeted or quantitative metabolomics. Untargeted is you have just the cell, you don't know what is happening with the cell. Take all the cells, run on a mass LC and GC based approach and do the data analysis and see what kind of a global metabolic profile of biological samples or metabolites you are getting about. So any kind of omics you have, targeted and untargeted metabolomics. If you don't know something, you will go to qualitative omics approach. If you know something which are you interested, single metabolite or a single protein of your interest, then you go for a targeted omics approach. So this is a very common phenomena in proteomic and metabolomic approach. You have an experimental design or a sample, you take that and you extract the sample and you do a pre-processing data. You run in like LCMS, NMR, GCMS, you have a data which will process, and you will identify through your metabolite analyst whatever kind of metabolite you are getting it, that you will map it onto that, and you see how it is upregulated and downregulated. You map it on the KEGG pathway, then that you can conclude your hypothesis, and then you can cross verify and experimentally validate what is happening and whether expected changes are there within the cell. That's how you answer what is happening within the cell when it is subjected to N plus and N minus condition, as I was talking about. So this is our experimental data where we have subjected to qualitative proteomics, where you can see number of metabolites which are upregulated and downregulated. This is upregulated and this is downregulated. You can see number of changes happening within that. These are number of metabolites which are upregulated, downregulated, and you can see what is the phenomena happening between n plus and n minus conditions, so that you can come to a conclusion. So this is how you can map onto that, and you can say you can put a hypothesis that what is happening at different conditions, and this is the overall hypothesis where color code says that red increases the number of metabolites. In red is the one which is upregulated, and the blue it is downregulated. You can see the one which is the most of the metabolic pathways in n minus condition are going down, such that the precursors can go towards fatty acid biosynthesis or tag accumulation. So if you are interested more, you can go through this latest paper in Biotechnology for Biofuels. The proteomics, similar kind of approach. I will not be dealing. So you have the cell tissue extraction of proteins, then separate the proteins by LCMS, and quantify the data and to project it, see what kind of proteomics approach. So this is the similar. You have the sample, you run on the trypsin digested, you run on peptide chromatography and DSI, and each MSMS can be identified, and the purified protein can be tagged upon the mascot to identify what kind of proteins are upregulating and downregulating. So, for example, this is an data which can represent the multiple proteins which are present. In our data, there are nearly 2,000 total proteins which are significantly upregulated or downregulated, and the common proteins which are significant changes when subjected to N minus condition is 166. Sorry, I'm going a little bit fast because of time constraint, but if any questions are there, I'll definitely like to answer. Finally, transcriptomics. There are different kind of transcriptomic approach, Illumina, ion torrents, and solid, because this is very important. Sources, what kind of in our lab we do Illumina transcriptomics to understand what kind of transcripts are upregulating and downregulating. So this is a transcriptome data of P. Kessleri when subjected to. You can see that the gene we have integrated these are the blue lines where genome and transcriptome. Overall lipid pathway is shown in pink. Overall metabolic pathways is shown in pink, and the blue line is the transcriptome data sets which are sent. So these are the genes, few genes which are related to lipid pathway, which are either upregulated and downregulated. So we have to validate what the transcriptome data is showing, so that you can look upon what are the kind of proteins which are upregulated. So as you said, like the CAR gene, ACC, BCC, all these genes are upregulating. So somebody was asking what kind of genes we should target. So in our organism, these genes are upregulating. So that is overexpression or underexpression. So if you want to prove it, we can delete that such an enzyme, and we can see that lipid is going down. So thus you can prove that thing. So we have hypothesized in a kind of a transcription regulation in this thing, and we can see that this is how the red pathway where it is being upregulated. This is where the transcripts are being upregulated, and you can see this is called half TCA when it is subjected to N-nitrous. Just the malate is recycled to malic acid to form a pyruvate. The pyruvate is recycled to form fatty acids. That is where the tag biosynthesis. So this is how the different transcripts are regulated. This is not up to any fold chain, but any fold chain which is happening, it can be consolidated, and you can see that how it is being regulated to produce a tag. So this is because this is the first whole genome sequence where we try to recently accepted in algal research. So this is a very important. This is a new technology where you used hybrid sequencing. That means we use nanopore and Illumina technology to understand this thing, and we have generated a 60 for genome size of 63 MB. Which consists of GC content around 55 to 60%, and we have around 8,000 genes which are mapped on using different parameters. So these the pink one is the lipid biosynthetic pathway, which is very much conserved. So we try to integrate all the data from genomics, metabolomics, proteomics, and all these things, and you can see that they are cross-talking and different phenomena happens with that. So in-depth things can be seen and visualized where particular genes are upregulated and downregulated. Thus, if you want to future modify or genetically engineer any pathway or a transcription factor, you can get an answer from this, and you can try to modify such that your carbon flux can be diverted to your desired product. So it should be very important to understand, because the parachlorella Kessleri is not reported, and this is the first kind of a report especially in marine microalgae, where we subjected all kinds of omics to understand that. So this is our thematic. So we will understand our biology through different multi-omics approach, and that will be put through systems biology and all this computational to reconstruct, and we can do the pathway engineering, and we can develop a microalgal cell factory by understanding the iomics through so that we can produce engineered cell factories which can be useful for producing of any desired products like biofuel, high value products. Finally, the fourth generation biofuels are nothing but, as I said, like we have a highly genetically modified that can capture the sunlight. It is grown on a solar conversion system. It is a dual technology which has been hypothesized, where you have number of like kind of photobioreactors which are being produced, and an industrial product is produced, and that can be separated, and you can produce either chemicals or fuel. The future of algal biofuels, and it's a non-agriculture land. You can use it, and you are growing in it, and you can capture in sunlight, CO2, all these things. In that way, highly engineering specific photosynthetic organism in a non-fresh solution can be used to convert into a desired product of your commercial product. So the fourth generation biofuels is the future of biofuels, and I think once we understand how to manipulate or how to do the things together to generate, and you can consider those things for biofuels. So this is the roadmap which is published in Algal Research in 2016 by Ankur et al. So this is NABB report, and it's freely available, and anybody can read it. So basically, I'll just go through this. What they try to tell is they selected a few microalgae, screened for them, and considered what is the best for biofuel. And so one main microalgae, which is called chlorella species, they have taken it for the further cultivation, to done the harvesting system to for magnetic the harvesting separated from the water using a filtration system called electrocoagulation process, where 95% of the algae was recovered. So what they have done is they have not included the feedstock or co-products in the production, but they directly converted into biofuel and seen that it can be the whole technology can produce a gallon at $7.50 at a price of that. Still, there are certain things like you add the co-product to this, you improve the harvesting process, cultivation process, this can still come back. So that you can make, thus you can make the biofuel the feasible product for the future. So that's why it's called, it's whether it can be sustainable in terms of, if you can work up on tails, you should have a considerable organism and co-products which can be produced, that can be substituted. Thus, you can say that this can be a sustainable process. So finally, I would like to thank all my students who are always in generating this kind of a data in order to have a kind of a approach where we can understand the details of a microalgae. And also, I would like to thank the funding agencies, DST, DBT, BIRAC, and Mission Innovation Program, where they constantly support us, inspire us to work on these novel areas to understand the biology. And thank you very much, and it's open for questions now.
Thank you very much, sir, for your this path-breaking lecture. And I would like to conclude regarding this particular lecture of Dr. Pawan Juthur, sir. He has elaborated very well regarding identification and characterization of robust microalgae from various collection for the genetic improvement for biofuel production. And he has delivered very good insight in the area of what is the role of genomic sequencing related with this microalgae, and for studying regarding pathway engineering. So these all type of information we have received from Pawan Juthur sir, so that we can also investigate related to lipid biosynthesis of the from the microalgae. So now this session is open for queries from the audience, so that Dr. Pawan Juthur sir will explain regarding your questions. So I invite Engineer R.P. Srivastava. Please, if you have some queries from the audience, please ask to the sir.
Thank you, sir, for giving me this opportunity. And the questions we have from the audience, the first question is, Difference, what is the difference between nitrogen repletion and depletion? If you can please again explain this. Thank you.
Okay. And nitrogen depletion is basically algae needs major components like nitrogen, phosphorus, and sulfur, right? Agriculture also we supplement nitrogen. Nitrogen is a major source of protein, right? So when you have a nitrogen depletion means when you remove the nitrogen from the media, it's called nitrogen depletion. So replete means when you put back the same condition back with all nutrients, the algae can survive back into a condition. As I said, when it is in deplete or any kind of nutrient is removed from the algal supplement, it is subjected to a stress. All the nitrogen, all the nutrient sources, it's called replete condition or nutritious condition.
Thank you, sir,
Okay.
for the answer. Next question we have. What is B3 algae?
Okay, B3 algae is basically you have that is a acronym for our group what we are working upon. So especially B3 means biomass, biofuels, and byproducts or biorenewables. So I was talking about like what are the different kinds of products you can produce by using sunlight, water, and nutrients. We can produce biomass, biofuels, and many number of biorenewables. That is very important for what we are looking for. That's why we call it as a B3 algae.
Thank you, sir, for the answer. Next question we have. Sir, what is the best culture media for growing green algae?
So you're talking about lab conditions. So usually in lab conditions, we use the best minimal media because for our omics studies, we try to have a minimal media because we have to understand the regulation of genes, transcripts, and proteins. So we try to grow it in a minimal media where we can give enough number of nutrients to understand. But the best media is the media what it is grown upon. For example, if you are talking about freshwater microalgae, you have a rich supplement acetate you can give, it grows very faster, it can be worked upon. So enriched media is the one which is required when you are doing in large scale production. So you can use different substrates like nitrogen source, especially urea or any kind of thing which are cheaper source when you are doing large scale cultivation. So in that way, enriched media is the best way. But when we are doing it at a lab scale, especially to understand the biology of that, you have to do in a minimal media because minimal media takes its own course of time to show the reaction. When you do enriched media, usually the cells grow at a faster rate, which is very difficult to sometimes capture the biological aspects or physiological aspects what is happening within the cell. Because in the cell, the reaction happens within pico or nanoseconds. So it's very important to capture the biological phenomena in these cells when we are trying to understand the omics of the algae. Okay.
Thank you so much, sir. This is the only questions we have from our audience.
Okay.
Over to you, sir.
Okay, thank you. I think we'll go to the next section if there are no questions. And I'm available, so I'll share my PPT or this thing. So you're welcome to ask your questions or something if you have, and you're welcome all, to clarify those things. Thank you very much for this opportunity. I would like to thank organizers, especially Kamlesh, Dr. Kamlesh, to give this opportunity to always interact with the students and the faculty at AKS University. And this is the best opportunity because sitting at our office, we are trying to interact with all the people throughout different places. So that's a great opportunity. And always we are here to assist you or help you in any collaboration. So
Thank you, sir.
our next, yeah, sure.
Very nice lecture, Kaksa. Very nice.
Yeah,
Thank
yes,
you, thank you.
sir.
Okay, so you need a break or we can just start it. I think we can start, right?
We can start.
Yeah. So our next eminent speaker is Dr. O.N. Tiwari. He is a senior scientist in Indian Agriculture Research Institute, CUBGA, Division of Microbiology at Pusa campus. And he is a reputed person who works on cyanobacterial algology and microalgae, and he has had many numerous publications in reputed journals in his expertise of exopolysaccharides, algal biology, and I would invite Dr. Tiwari to enlighten with his research today.
Shall I start, Doctor?
Yes, please, please.
Arpit, may I request you please guide to the sir related how can we start the presentation?
Sure, sir. So, sir, on the right side of your screen, there is a fourth icon. That's a small picture-based icon.
Which icon?
Sir, fourth icon on the right side of the screen.
Right side on the screen.
That is a small icon, fourth icon.
एक पिक्चर जैसा दिखेगा सर, पिक्चर जैसा शेयरिंग ऑप्शंस करके.
Just you show me the sharing option, I will share.
So that is
sharing options.
Dr. Arpit?
Sir, on the right side, see the fourth icon. On the top, it is a red button. After that, we have the count number 1, 2, 3, and the fourth one.
Sharing option, yeah.
Yeah, just click on that.
Yeah.
Now it will ask you to add to Chrome. It will ask for an extension to add to Chrome.
Step number 1. Add blue gene extension.
Yes, sir. So once it is get downloaded, it will add up to your Google Chrome extension bar.
Add to Chrome. It's downloaded.
Okay.
Yes, yes.
So now it will automatically it will show you here on the icon on the top corner that it is already added. Now again go to the sharing option. जहां सर आपने पहले क्लिक किया था उसी आइकन पे फिर से क्लिक करेंगे. Sir, your extension is no sir. Sir, your extension is downloaded. Now again back to the sharing option जहां आपने पहले क्लिक किया था सर.
Sharing screen sharing with meeting parties. Not coming.
फिर से शेयर स्क्रीन पे क्लिक करिए.
कौन सा स्क्रीन?
शेयर स्क्रीन.
पहले स्क्रीन शेयर पे आपने क्लिक किया था, अगेन उसी पे क्लिक करिए. आपका एक्सटेंशन डाउनलोड हो गया है सर.
Add blue gene extension. Shall I click add blue gene extension?
Yes sir. Yes sir.
Yes.
Yeah. After that?
Now at below you can see that it is downloaded.
Downloaded.
नीचे सर वो डाउनलोड हो गया होगा. It hardly takes 30 seconds to download.
Oh, it's not downloaded. And bottom it is coming. This extension enhances the blue gen experience for Chrome users. But downloaded is not showing.
Oh,
So I
Sir,
think
sir, I think it is added in your Google Chrome extension list. Sir, please restart. Please restart your this window of this particular presentation share screen options.
Okay.
Just close it. Screen share option just click करिए दोबारा आएगा.
Share screen. I have clicked.
Yes.
In
Yes, sir.
share screen.
Then entire screen.
Yeah, I am able to see Dr. Pawan Jutu's picture.
Entire screen. Then select entire screen. Is it coming, sir?
No, it's not coming.
नहीं when जब आपने क्लिक किया शेयर स्क्रीन वाले ऑप्शन पे तो वो विंडो आई होगी एंटायर स्क्रीन सिलेक्शन के लिए.
नहीं आ रहा है. I don't know where is the problem. Shall I share my PPT too and you share from your end?
Yeah, we can share it, sir. So please mail me
yeah,
that PPT.
that's the best idea.
I'm just mailing to Dr. Pawan.
Yeah.
Participants, please bear with us. There's a small technical issue, so we'll just come back within 2 minutes.
सर आपने मेल से कर लीजिए, आपको मैंने शेयर कर दिया है.
अच्छा अच्छा, श्योर. जीमेल पे भेजा है ना सर?
ईमेल में जी. First time today I'm using the blue jeans. Actually, we are using MS Team for our courses classes.
Oh, okay. Yeah.
MS Team and Zoom. We are
Oh,
regularly.
right.
First time I tried jeans, but jeans, but
Yeah.
regularly using the MS Team and Zoom.
हम्म हाँ आ गया सर ठीक है,
आ गया है?
आ गया
आपने जहां पे शुरुआत किया है हम उसके पीछे और आगे दोनों कवर करेंगे.
ओके श्योर श्योर
ये बड़ा
Thank
लेक्चर
you,
दिया.
sir.
It's very knowledgeable.
so I'll just try to start Dr. Sir आप next बोल दीजिए so that I can go to the next slide. So
Yes,
now I'm starting.
Yeah, please.
So hope you guys are seeing the slides. So
Yeah.
Yes, sir.
I able to see.
sir you can carry on.
Yeah. Good afternoon to all. And I guess I am a last speaker of this event. Yesterday
Howdy.
and today, Dr. Pawan Jutur covered a lot from basic to omics. But I would start from the basics as the title of the biotechnological potential of microalgae biomass for multifaceted products. I am underlining this word multifaceted products including biofuels. So under my talk, I will cover one component of the what are the microalgae, what are the cyanobacteria. Then second component will cover the biofuels because the main theme of this program is the biofuels. And third part, I will cover the co-products. As Pawan Jutu Saab already spoken something, so I will cover in detail, particularly taking the strains of Chlorella, Senadesmus, as well as the Spirulina. So here you can see there are some pictures of the microalgae, some culture collections picture, some productions picture for the biofuel. One by one, I will talk and cover all these aspects within 45 minutes. Yeah, see. Okay, sir. Next, please. First of all, I would like to apprise to the experts as well as the attendees who are listening. These are the 4 big algal centers established long back, almost more than 100 years in the country. Banaras Hindu University, Tamil Nadu, IARI New Delhi, where currently I am working, and Allahabad. These are the 4 renowned centers. And you can say the excellent school of the phycology or algology in the country. Banaras Hindu University, it was Dr. Y. Bharadwaja, Aryan Singh, YSRK Sharma, H.D. Kumar, D.N. Tiwari. They are the Tory persons and established a strong school of phycology and Banaras Hindu University. Still in Department of Botany, Banaras Hindu University, people are working in very depth on the algae from basics to advanced studies. Tamil Nadu, those who are working in the algae field probably aware that M.O.P. Iyengar, who is designated as the father of Indian phycology, started algae school, phycology school at University of Madras. And the legendary was T.V. Desikachari, Yan Anand, G. Subramaniam, G. Shanmuga Sundaram. They are from the Tamil Nadu, Dr. Iyengar, Desikachari, Anand from the Madras University, G. Subramaniam established a very strong marine algae center with the help of Department of Biotechnology at Bharati Dasan University, Trichy. G. Shanmuga Sundaram was the professor at Madurai Kamaraj University. Then IERI New Delhi, Dr. G.S. Venkatraman. Currently, I am working at IERI New Delhi. The center was established by the G.S. Venkatraman, followed by the S.K. Goyal, P.K. Singh, B.D. Kosi. Then Allahabad Center. Allahabad Center established by the Dr. A.K. Mitra, D.C. Pandey, V.K. Laloria, G.L. Tiwari. Here I would like to mention one thing. Long back, almost in 1986-87, Department of Biotechnology, Government of India established 2 algal centers in the country, one at IRI New Delhi, which was exclusively for the maintenance, characterization, blah blah, for only for the freshwater algae at IRI, and simultaneously same times another center established at the Bharati Darshan University, namely National Facility for Marine Cyanobacteria, and Dr. G. Subramaniam started the centers, and now center is the best marine centers in the country. These are the 4 renowned centers, particularly for the basic research on the different aspects of the algae. Although there are so many centers, so many universities, so many research organizations working on the algae, but these 4 centers are established by the Tory algologists for the basic to advanced research in the different aspects of the algae, including cyanobacteria, microalgae, everything. Here you can see 2 pictures. One is the spirulina and another one is the spirulina, and another is the Oscillatoria limosa. Probably you people are very much aware about the spirulina pratensis, and I will talk 10 minutes on the spirulina pratensis in the third part of my lecture. And another is the Oscillatoria limosa. This Oscillatoria limosa we have established at our culture collection, which is equally good to the spirulina pratensis, but we have to go for the long path for the commercialization of the Oscillatoria limosa. These strains we have isolated from the freshwater habitat from the northeast region of India, Manipur, and we got a equal type of the phycobilly proteins, and recently last year we published good papers, more than 8 impact factor. So these are the 2 pictures which we are considering. One is spirulina pratensis, already commercialized. Oscillatoria we are trying to commercialize because we are considering these particular strains are very useful for the commercial exploitation. Next please. Yeah, current areas on the microalgae research. As you know, microalgae is covering both cyanobacteria as well as the other algae, which are the microscopic microalgae. Current areas on the microalgae research is the conservation and preservation. Until unless you don't have the facility or you don't have the knowledge how to conserve and how to preserve, it's not possible everyone to go to the field, collect the sample and do something and remove. It's not an easy task. So first we have to learn about the conservation and preservation for short-term goal as well as for the long-term goal. I will cover in the later on what methods we have to adopt for the conservation. Then the second component is the bioenergy, biofuel from the microalgae via biorefinery approach. Although Pawan Jutur also said our approach should be the biorefinery approach, because if we are cultivating any quantity of the biomass, then we have to utilize as much as possible. That is the biorefinery approach. Suppose if you are cultivating chlorella or synedesmus for the biofuel purpose, then we must think we have to go for the other utilization, other co-products also, because we are not going to cultivate for the other purpose. So this is the simply the biorefinery approach. Then after knowing their production capability and other things, then we have to think about the biomass production, either by the nutritional using the nutritional factor or biochemical factor or any kinds of the omics. We have, until unless we have not developed good technology for the large scale cultivation and biomass production, probably we may not reach as per the need of the nation and international. That we have to go for the identification and characterization after knowing that if this X or Y strains are very, very suitable for X or Y purpose, then first we have to go for the correct identification. As you know, there are the too many tools for the identification, from the microscopic to other recent molecular methods. Simultaneously, we have to think about their usage as the biofertilizer, their usage as the proteins for the dietary supplements, high-quality proteins for the natural colorants. As you know, every day we are talking about the chemical colorants. Most of them are very harmful for our body if you are taking as a Nutra or the Pharma in any way. And other beauty of the natural colorant, they are safer for our body, as well as all 5 quality proteins are the proteins only. So they are providing two things. One, if we are intaking, we are getting the good amount of the proteins as well as the colorants. It is the natural colorants which are not going to harm to anyone. And other components is the carotenoids. Carotenoids, as you know, is the vitamin A precursors, and cyanobacteria and other microgreen algae are the good source for the production of carotenoids. And next is the exopolysaccharides for the pharma and bioremediation, along with the agricultural productions. So these are the area where nowadays worldwide focus is going on, but approach is entirely different, person to person, lab to person, lab to lab, or the organization to organization. But these are the area where people are working using the tool as a cyanobacteria or the microgreen algae. Next. Role of the cyanobacteria repository, as I said, long back DBT started 2 algal facilities in the country. One at IARI New Delhi, which is exclusively for the freshwater cyanobacteria, and another is marine cyanobacteria. For the marine cyanobacteria, a center was established as the Bharati Rastan University. Dr. Pawan Jutur is very much aware that before joining to IRI, I worked almost 11 years in Northeast region in a DBT institute from 2004 to 2016, where I established one national repository for the cyanobacteria and microgreen algae, and we established more than 1,500 cyanobacteria and microgreen algae from all 8 states of the Northeast region. But what is the main role of the any repository? Doesn't matter if it is from the Delhi or from the Manipur or from the South India or worldwide. The main component or the role of the any repository is first to isolation, identification, and strengthening of cyanobacteria germplasm. Every day we have to add something. Then only we have to increase the number. In between, in 2012, I got the opportunity to work at a visiting professor at University of Texas at Austin in UTEX. There I worked almost 6 months there. And UTEX is the largest algal culture collection in the world. They are maintaining more than 7,000 cyanobacteria and microgreen algae, and also they are every day adding 1 or 2 the students or the any persons who are coming by their system for the working for 3 months, 6 months, or 1 year. The first target they are fixing, you have to contribute some good number of the algae, maybe 2 or 5. So that's why they are doing very good business, selling, organizing training, workshop. Then they are enhancing the number of the cyanobacteria and microgreen algae. Second role of the repository is the cyanobacteria isolates are constantly being added. Correct, not only the number, increase the number, it should be correctly characterized are the various attributes covering the pharma, nutra, or any biological components. Third important component, which is very, very important, is the supply of cultures to the researchers and entrepreneurship. Otherwise, there is no meaning of the establishment of the repository from the public fund unless there is not a fixed mandate to any repository to supply to the cultures to the researchers and entrepreneurs. Of course, following the rule and regulation, particularly the if it is going to the entrepreneurship or something, there is a certain rule of each repository following the guidelines of the National Biodiversity Authority. So these are the three main role of the cyanobacteria. As I said, then after the isolation, identification, characterization, whatsoever, we have to go for the short-term and long-term preservation of cyanobacteria on agar plants. This is the very common methods. Immobilized alginate beads, cryopreservation, and lyophilization. These I will cover in the next slide. So we have established a technology for the short term as well as the long term. So here you next. Yeah, see, maintenance and preservation. Maintenance and preservation are the these two are the communicating different meaning. Maintenance should be in the culture room and preservation should be in the repository. Maintenance, you can see here the maintenance condition of culture room and maintenance condition of the alga repository. Culture room means where you are cultivating algae or cyanobacteria for the any experiment purpose. Then you must maintain the temperature 28 plus minus 2 degrees centigrade, light intensity 4 to 5 K lux, light dark period 14 to 10 hours. This is the biology, needed biology of the cyanobacteria if you are cultivating for the any experiment purpose. If you are preserving your cultures for the long term in the repository, here you can see the comparison. Temperature is minus 19 plus 2 degrees centigrade, light intensity 1.5 K lux, light dark and humidity. Why it is the temperature is 19 and light intensity is 1.5? Because here we are not doing any biological research in the repository. We are just preserving agar plants or the broth for the longer period. If we are cultivating the same algae in the culture room, maintaining the temperature 28, light intensity 4 to 5, probably after 1 or 1.5 months, culture may be going to dry. But if you are maintaining the temperature 19 plus 2, light intensity 1.5, the same cultures you can preserve for the not less than 6 months. That may give you some more time to do, reduce the manpower, reduce the chemicals, expensive chemicals. But most important things, we have to think about the cryopreservation. If you have to develop a cryopreservation technology using the glycerol, DMSO, and methanol techniques, you can preserve your cultures more than 5,000 years. But I would like to communicate here all cyanobacteria or all microalgae are not suitable for the cryopreservation. Please note down this one. Cryopreservation is two-way. One, you have to preserve in minus 80 degrees centigrade freeze or in minus 190 degree in liquid nitrogen facility. But before going to preserve for cryopreservation in minus 80 or 196, first you have to check the revival rate. Otherwise, if you are putting without knowing the revival rate, it may be lost all your cultures. I would suggest here first you have to put 10-20 cultures on trial basis for 24 hours, get back from the deep freezer or from the minus 1 liquid nitrogen facility. Then you have to again go for the cultivation. If you are getting 60% revival rate, that may be the very good rate. So it's not a viable decision to go for the cryopreservation all algae at one time. first you have to check the revival rate, then only you. If suppose if it is 60% out of 100, if 60% is capable to revive, that will be the great research. And then you can preserve your cultures for the 1 year, for the 10 year, for 20 years, for unlimited time. This is the beauty of the cryopreservation. Next. Next, please. Yeah, microalgae and their advantage, Dr. Pawan already covered, but I would say add something here. What is the beauty of microalgae? What is their advantage? The group microalgae comprise of both prokaryote and eukaryote. Thylophytes prokaryote or cyanobacteria falling under the prokaryote. Chlorella and desmasa, they are the eukaryote. But either they are prokaryote or eukaryotes, but falling under the thylophytes. Thylophyte means those algae are not divided into root, stem, leaves. You can say microscopic. So microscopic organism. And these photoautotrophs, as you know, they are evolved 3.5 billion years ago. Long back, the oxygen which was released in our atmosphere came only from the cyanobacteria, and it was around 3.5 billion years ago. And they dominated in our Earth almost 2 billion years. So found in aquatic habitats predominantly with quite a few abounding subaerial and aerial niches also found to grow as the thermophytes and cryophytes. This sentence is communicating that they are ubiquitous distribution. Cosmopolitan distribution, ubiquitous or cosmopolitan distribution means they are capable to grow and survive anywhere where life is possible, although their growth rate may increase or decrease, but this is the beauty of the microalgae. They can survive in any kinds of the environmental conditions. So thylus organization, as in the second point I said, they are the thylophytes. Again, thylus organization from a motile unicell to most complicated corticated polyaxial type. So they are from the unicellular to multicellular, or individual, colonial, multicellular, filamentous, then filamentous to non-heterocystous, heterocystous. So they have the diversity. And what is the other beauty? Higher photosynthetic efficiency, faster growth, and larger biomass. Easy mass culture, easily controllable environmental conditions around the year production, non-polluting and environment friendly. These are the beauty of the microalgae and their advantage. Dr. Pawan Sahab already said that the other beauty of this group is they are not going to compete with our agriculture land. They are not going to compete with our water resources, because day by day our agriculture land is sinking, and some parts of the world as well as even the India, water, even the drinking water is a problem. So if other than the algae, if you are going for cultivating for any purpose, probably it may not going suitable for the saving our agriculture land or the water, because the water which we are using for the cultivating of microalgae is the recyclable, reusable. So there is no much problem with the land as well as the water. Next. These are the microphotographs of selected microgreen algae, and they are useful. See, from the unicellular to colonial. They don't have the filamentous, because if microgreen algae are the filamentous, we consider they are not microgreen. Microgreen means unicellular up to the colonial. If it is filamentous, I am talking about the eukaryotic algae. Eukaryotic algae, if it is they are filamentous, we consider they are not microgreen. Up to unicellular and colonial eukaryotic algae falling under the microgreen algae. So here you can see these are the microgreen algae, and they are useful for the biofuel as well as the other co-products too, that I will cover in the next. Next, please. Next slide, please. Back. Yeah, see here. These are the other slide mode. Yeah. Here you can see these are the second slide of the microgreen algae. Again, you can see all are the unicellular or in the colonial form. First slide is the Chlamydomonas, Botryococcus, Chlorella, different species of the Chlorella, Dictyosporium, then Synedesmus, Lichneria. They are these cultures are available with our facility, and we are maintaining, and they are also useful for the biofuel purpose as well as other co-products too. Next, please. Now I'm coming with the cyanobacteria, first, second, third, fourth. As you can see, they are the not photomicrographs, they are the colony growing in the nature, but in undisturbed conditions. If someone is disturbing, the colony may not reach up to 2 inches. So here in second, third, and in fourth line, you can see these are the unicellular cyanobacteria. And the last two pictures in the right direction, they are the filamentous cyanobacteria, but they don't have the heterocyst, they are unbranched. Others are the unicellular and colonial. Here you can see colonial cyanobacteria. Next. Yeah, again, from primitive to advanced, here you can see the spirulina pictures. Then they are the non-heterocystous forms. Here easily you can see the heterocyst, achainids. These are the structures, and these heterocystous forms are very, very useful for particularly for the biofertilizer purpose, as well as they are also useful for the other industrial co-products too. Next. Yeah, now come to the chemical composition of microalgae. Now I am directly coming to the biofuel as well as the other co-products from the microalgae as well as the cyanobacteria. Here you can see chemical composition of microalgae, Synedesmus, Chlorella, Dunaliella, Spirulina, and Synechococcus. First, second, third, and fourth are the microgreen algae, Spirulina, and Synechococcus are the cyanobacteria. Here the protein content in Synedesmus around 50 to 56. In one species, see the differences. In one Synedesmus species, protein content is 56, and in another species, Dimorphus, 8 to 18%. So that's why I said, if knowing something about the potentials of the microgreen algae, we have to go for the correct identification, because all Synedesmus species looks like the same way. And here you can see the differences of the protein content. In one species, it is 50 to 56, and another species is 8 to 18. Then we need correct identification using all modern tools and techniques if we are going to characterize for any purpose, any industrial purpose. Carbohydrate, here you can see if protein content is higher, obviously carbohydrate content is lesser. In second Synedesmus species, here you can see protein content is lesser than carbohydrate content increase. Lipid content is here in Synedesmus 12 to 14. All value are in the dry weight basis only. And here, so out of two species, I can say one Synedesmus species is good for the proteins, and other Synedesmus dimorphous species is good for the lipid. That's why I am emphasizing, unless we don't have the correct identification of the strains from the basic to advanced level, probably we may not justify our claims and our research. So here again you can see the chlorella vulgaris protein content is around 51 to 58%, carbohydrate like this, lipid content maximum up to 22. Dunaliella again is for the proteins higher but not suitable for the lipids. Spirulina maxima is 60 to 71% and already commercialized strains. Synechococcus is also good. So out of these, I can say Synedesmus dimorphus is very suitable for the lipid production, and Spirulina maxima, Synechococcus is very suitable for the protein content. But as we know that most of the cyanobacteria having the toxins. So if you are thinking about the nutra and pharma purpose, then we have to check other components too, particularly the toxins. Particularly in spirulina case, it's already discovered, and WHO, after knowing all the facts, declared as the best nutritious organism in the nature. That's why there is no question on the spirulina maxima. As I said in the previously, we got a very good strains oscillatoria, which is comparable to the spirulina maxima, but we have to check other components also if you are claiming that oscillatoria hemocyte suitable for the any biotechnological applications. Single cell protein, spirulina maxima is having the single cell protein, excellent digestibility, provides essential amino acids, vitamins and minerals, feed for fish, cattle and poultry. These are the feature of the spirulina maxima. For other algae, we have to check it thoroughly. Microalgae, next please. Microalgae as a nutrient supplements. Microalgae like Anabina, Enkystodesmus, Chlorella, Synedesmus, and Spirulina afford easily manageable source of cheap protein, minerals, and essential amino acids. The biomass conversion efficiency of microalgae is 18% as compared to only 6% of the crops. See the differences, and you can compare if you are talking about the lipid purpose. This is because of the microscopic size, which increase the surface area. These can be grown round the year, require less area, and have simple, easily available, cheap nutrients. The entire biomass can be used without any processing. This is the beauty. The versatile energy conversion, less capital investment, more production per unit area, and is offensive and ecologically safe nature of the production unit make the microalgae as the most promising protein source of future, not only for the protein as well as for other nutra and pharma products too, along with the biofuel. Next. Other value-added products from the other microalgae, glycerol. Dunaliella is very good source for the production of glycerol. Dunaliella is a unicellular halophytic microalga and cells are divided of cell wall. It can grow in the presence of 0.5 to 35% salt concentration and forms richest source of high quality products like glycerol, carotenoids and proteins. Some species of Dunaliella can produce beta carotene to the tune of 10% of the dry cell biomass. Most of the beta carotene is accumulated in the lipoidal globules located in the interthylakoidal space of the chloroplast, in contrast to the higher plants where it is stored in the chloroplast. So this is the beauty of the another microalga known as the Dunaliella. Next. Chlorella, a microgreen alga, is a unicellular non-motile alga. Has been the most exploited source of single cell protein. It contains up to 50% protein on dry weight basis. Synedesmus and Enkystodesmus are other green alga next to chlorella. So from the microgreen alga, these are the well exploited chlorella, synedesmus, and schistodesmus are the biotechnological potentials. But again, I would precautions here being eukaryotic. All these are the either the chlorella or the synedesmus or the schistodesmus or the dunaliella. They are the eukaryotic alga. So being eukaryotic, these contains high amount of nucleic acid. And if nucleic acid intake is beyond 2.6 gram per day, the uric acid content of human urine crosses the safe limit of 4.5 to 5.1 microgram per 100 ml. Cell walls are made up of cellulose which cannot be digested by human digestive system, and increased intake leads to gastrointestinal problems. This is the precautions. So we have to be very realistic, and we have to intake as per our need, not like if they are having the very good protein or some other components and we may take as much as possible, not because they are the eukaryotic and they may sometimes harm to our body. Next. Yeah, now biofuel. Hypothesis for the utilization of algal biomass for the multifaceted products at a glance. The cyanobacteria or the other microgreen algae, doesn't matter if they are the prokaryotes or they are eukaryote, but they are common in line of the photosynthesis. They need water, they need CO2, water, CO2 as well as the sunlight and some inorganic fertilizers. Then they are able to go for the photosynthesis. This is the biorefinery approach. Dr. Pawan Jutur covered a little more in detail, but here I would cover only. If we are cultivating any amount of the biomass, then if you are utilizing for the one or other purpose, that is the biorefinery approach. So here you can see we can extract lipids like the hydrocarbons, biodiesel, feedstock, nutraceutical, pharmaceutical from the same cells. Then simultaneously we can go for the extraction of the proteins for the feedstock, nutraceutical, pharmaceutical. Simultaneously we can go for the carbohydrate for feedstock, nutraceutical, bioethanol. These are the beauty of the any prokaryotic or the eukaryotic microgreen algae. If we are approaching biorefinery way, so same biomass may be 1 gram or 100 gram or 1 kg or 100 kg. They are all having the potential. So we have to utilize in a biorefinery approach. So in the same time we may get so many things, so many products, co-products from the same biomass. This is the I consider biorefinery. Next. Energy. Energy is the renewable energy source, is the hydro, solar, wind, and bioenergy, which reduce consumption of fossil fuels, GHG emissions, greenhouse gases, of course. Biofuels is the biorefinery, biodiesel, and bioethanol. But is again I am repeating the same things. Why we are advocating cultivation of microalgae for the biorefinery for the energy purpose? Because they are environmentally sustainable, because they do not compete with other food crops for arable land and water, not commercialized or viable due to higher production cost when compared to fossil fuels. This in 2 lines I have cleared the merit and demerit of the microalgae. Merit, they are not going to compete with our agriculture land, they are not going to compete with our drinking water. But why they are not so much popular or so much useful till date? Because production costs are very higher than the fossil fuels. Next. Cultivation. There are 2 systems already established, open raceway pond and photobioreactor. But again, the beauty of merit and demerit of both systems, if you are cultivating open raceway ponds, then capital cost is not very expensive. This is the beauty. Problem with the open raceway pond system is there may be chances for the contamination. particularly if you are cultivating for the nutra or the pharma purpose. Because for nutra and pharma, your biomass should be 100% pure. Second is the photobioreactor under natural or artificial illumination. Capital cost required high. This is the drawback, but merit of the photobioreactor culture or whatever you are cultivating, they are having the pure. There is no chances for the contamination because everything under the control. So cultivation system both having the merit and demerit. Open raceway having the merit, you can cultivate as much as possible. Capital cost is very less, but chances for the contamination. Photobioreactor, capital cost is higher, but most beauty is biomass unialgal. So you can use for the pharma or in the nutra any purpose. Higher capital cost and operating expenses, but helps in the maintaining pure culture. This is the beauty of the photobioreactor. Higher capital cost, operating expenses, but helps in maintaining pure cultures and results in higher photosynthetic efficiencies. Ensures higher cell concentration, improved CO2 utilization efficiencies, and enhanced volumetric production. Next. Microalgal biodiesel, I will not speak much because Dr. Ponjutur already covered, otherwise it will be the repetition. Although words are different, but he covered entirely. I will speak very less. Microalgal biodiesel is highly dependent on the lipid content. Biodiesel is defined as the monoalkyl esters of fatty acids paired by trans-esterification of algecerols. It can be used in diesel engines in any proportion when blended with diesel without significant engine modification or even with no modification at all. Algal lipids chemically similar to common vegetable oils. Triglycerides, major constituents of microalgae lipids, can be converted to biodiesel. Biodiesel production is the two steps: trans-esterification and esterification. Bioethanol production from lipid extracted residual biomass by esterification and alcohol fermentation. This already Dr. Pawan covered. So next, please. Yeah. What we did, as I said, we established more than 1,500 microgreen algae and cyanobacteria, and it was very, very difficult to run all the samples, 1,500 samples on the GCR, GCMS for the cleaning purpose, particularly for the production of biofuel. Then we started with the Nile dead methods. For the Nile dead methods, we need the only fluorescent microscope. So number may increase because after showing their filaments or the biomass under the fluorescent microscope, you can easily understand which out of 10 or out of 100, which one or two are very, very useful for the biofuel purpose. Then only we have to plan for the detailed characterization. So this was our methodology. We cultivated, then we have tested for the Nile dead methods. After knowing that particular strains are having the potential, then we have analyzed using the GC and LC soft liquids. Next. Here is the Nile dead methods. You can see this is the procedures which I have mentioned, which we have utilized. Out of these 6 pictures, you can see there are the two kinds of the droplets. One is the yellow color and another is the red color. Yellow color is actually the lipid and red is the chlorophyll A. After seeing, but you have to have the fluorescent microscope. Out of these 6 pictures, I can easily say last one is very, very suitable for the biofuel purpose, because the yellow color, yellow droplets showing the. So in this way, we can easily screen even the 100 strains out, and we can come to the conclusion that out of the screen, which one is suitable for the detailed characterization. So Nile dead method which is the staining method is suitable for the screening purpose if you are maintaining many strains and thinking that you have to go for the detailed characterization. Then my suggestion, first you have to screen using the Nile red staining methods, then go for the other. Next. Microalgae and bioenergy. Here, bioenergy producing biodiesel from algae is widely regarded as one of the most efficient ways of generating biofuels, and also appears to represent the only current renewable source of oil that could meet the global demand for transport fuels. Second generation microalgal systems have the advantage that they can produce a wide range of feedstock for the production of biodiesel, bioethanol, biomethane, and biohydrogen. So this is the again beauty of the microalgae. They are useful for the all kinds of the products and co-products. Dr. Next, please. Potential of microalgae for biodiesel production does not, I have already said, it's not going to compete with our agriculture and water. And here some environmental factors I would like to cover. CO2 generated from electric power unit can be used for photosynthesis. Hence, the CO2 emissions can be reduced. Agricultural and municipal waste runoff can be used as a source of nutrients, ammonia, phosphate, and nitrates for the growth. This would facilitate the cleaning up of the nutrient-laden effluents. Growing algal biomass can be harvested from eutrophic lakes. Biomass thus produced can be used for biodiesel production. After the presentation of Dr. Pawan Jutur, some people have asked the best methods for the large-scale cultivation, and Dr. Pawan Jutur said, here I would like to add, other than commercial media or the designated media, there are other sources for the large-scale cultivation of microgreen algae. But first, we have to check all these things. Next. Mass multiplication in fast foods. We have to start from the, as I said, we have to go by step to step. So this is the small scale productions in the laboratory. Next, please. Don't need to go further. Here, raceway pond production. You can cultivate here. Next. Because in first, in cemented tank, large scale cultivation, you can say. So I would suggest first you go step to step from smaller scale to larger scale after getting the experiences. So this is the cemented tank production. Next. Here you can see cultivation in the photobioreactors, field level, big raceway ponds. Next. Here. SLT for the cultivation. Then methods for the harvesting. Methods for the harvesting, which is very important because still people are suffering to develop a foolproof harvesting methods. So there is the centrifugation method, micro screening methods, flocculation. Flocculation is two types, is the bioflocculation and co-bioflocculation. These are the methods still people are using for the harvesting. Still worldwide people are facing to develop foolproof methods for the harvesting of desired biomass. We never speaking like this, we have to harvest 100%. We have to harvest at least 80 to 85%, remaining 15% we have to leave in the system as a seed materials. And the water, this is the beauty, we are not going to use seed or the cultures after every harvesting, or we are going to change the water after every harvesting. We have to use, reuse, recycle. So that's why they are not going to compete with the drinking water. availability of the drinking water. Next. Methods of the oil extraction. Expeller are the press, superficial fluid extraction, hexane solvent methods, osmotic shock, enzymatic extraction, ultrasonic assisted extraction. These are the methods applied by the different peoples for the extraction of the oil. I am talking about the oil, not other products. Next. So my last component, last part is coming. My lecture, as I said, but I know I will take another 5 to 7 minutes and complete my talk. Spirulina, as I said, spirulina is the best nutritious organism in the nature, and WHO declared this because spirulina having all the desired components like the protein, carbohydrate, gamma molecule, everything is available in this spirulina. Why it's spirulina? Because it looks like the spiral, like the snakes. That's why it's known as spirulina. Although commercial name of this organism is the spirulina, but the botanical name is the Arthrospira. Don't confuse what is the Arthrospira or the spirulina. Commercial name of the product organism is the spirulina, otherwise is the Arthrospira. Next. These are the some growth of spirulina pretenses. These are the growth of the spirulina from rural. These pictures are from the rural areas, from the tub, from the bucket. If there are no big facility available, so one can cultivate for their own purpose in the plastic bucket, tubs, even in the Hopkins flask for the experimental purpose. Next. The commercial possibilities of spirulina in pharma and nitro aspects. They are having the good amount of the proteins which are the vital for growth and development, vitamin B complex for effective metabolism of nutrients, iron helps in the formation of hemoglobin, calcium for healthy bones and teeth, phycocyanin strengthens the immune system, antioxidants slow down the aging process, GLA controls cholesterol, improve skin tone, beta carotene produces vitamin A, which is good for the eyes. That's why we consider superfood in the nature. You can't get all these things in one place. Next. Commercial products available worldwide. Here you can see thousands of products available worldwide on the base of the spirulina. Some of the companies of spirulina doing business in India is the Perry Nutraceutical, Sanat Products, Blue Nutritional Products, Dabur Limited, Good Care Pharma, Bonder Herbs, Tan Horde Exports, etc. In our country, spirulina research started at CFTRI Mysore under the leadership of L.V. Venkat Raman and his associates. So all credit goes for the initiating of the spirulina as a biotechnological tools from the CFTRI Mysore. Next. These are the some companies producing, selling, marketing. Yes, Pharma International India, spirulina and aloe vera capsule, Tan Horde Exports India, spirulina capsule, Bonder Herbs, spirulina dry powders, health food, Sanat. These are the leading companies doing business on the spirulina products. Next. See here, the open door production of spirulina biomass for the commercial exploitation. You can see how much people are cultivating. This is the pictures which I took from the spirulina cultivation facility at Florida when I was there. Next, I'm coming. Nutrients and the other chemicals. Microgreen algae or cyanobacteria, particularly spirulina, having good source for the protein, vitamins, minerals, pigments. I have covered all these things. Next. It is not permitted. Next. Therapeutic usage and chemopreventive applications, they are useful for the back slides. They are useful for the diabetic, anti-allergic properties, arthritis, antibiotic related illness. And that's why I said superfood. Next. They are also used for the oral cancer. But I would suggest here, no, don't go blindly unless you have to recommended by the experts for intake of any kinds of products, spirulina-based products available in the market, because everybody is having their need. So first you have to consult with the physician, then only you have to take as per the recommendation, dosage, amounts, durability, everything. You have to discuss with your physicians, then only you have to go for it. Next. Microalgae as a biocontrol agents. Now I will speak another 2 minutes on the agriculture aspects. They are useful for the agriculture biocontrol agents also. Next, please. Particularly the chlorella and Farmedium pectonema. They are useful in the pharmacy. Chlorella, Cytonema, Farmedium, Dimbaya. They are good. So dicotyledons, they are good source for the pharmacy. Next. Usage in agriculture activity. This is the last part. Spraying of trees or crops with nitrogen fixing and improving the quality, color, sweetness, vitamins. As I said, your cyanobacteria has very, very potential for the biofertilizer purpose. Earlier it was educated for the only for the rice crop, but now boundary has crossed. Cyanobacterial biofertilizer useful for the rice as well as the vegetables or for any purpose, they are potential, particularly in rice. If you are cyanobacteria biofertilizer used, production of the rice may increase around 15 to 20%. Next. Effect of soil health, as I said, cyanobacteria releasing, having so many improve soil structure, improve soil fertility, and promote crop growth. A large number are nitrogen fixing, having the ability to improve soil nitrogen levels, soil composition of some organic sulfides, ammonia, nitrogen, and the promotion of harmful pollutants. At the same time, can a beneficial microorganism can generate a wealth of physiological activity. Substances like carotenoids, which can be absorbed directly and can help to improve crop nutrition and promote root development, enhance photosynthesis, growth, and reproductive capability. These are the beauty and they are harmful aspects. Blooms of freshwater algae is the harmful, red tides and marine blooms, toxins accumulated in food chains, fouling of ships and other submerged area, as we are aware that if some is having the merit, then simultaneously there are the demerits. So these are the demerits of the algae if they are growing in a large amounts in any ecosystem. Next. Last. Beneficial aspects of algae, I will conclude with this slide only. Foods for humans, food for invertebrates and fishes in mariculture, animal feed, soil fertilizer and conditioners in agriculture, treatment of wastewater, hypocolloids, drugs, model system for research, phycobiliproteins for fluorescence microscopy. Next. I am thankful to my authority but permitted me to deliver the lectures, Department of Biotechnology, Government of India for the funding, and most importantly, authority of AKS, University Satna, for giving me a platform to talk my research, my thought on the cyanobacteria and microgreen algae. Particularly, I am thankful to Dr. Pawan Jutu, who is the coordinating of this program and recommended my name as a speaker for this session. Thank you very much.
Thank you, sir. We'll have two questions because of time constraint, and we have a last speaker of day today. So, can you, if there are any questions, please, we'll have two quick questions.
Thank you so much, sir. Yes, we have some questions, and the question is from the attendee: how nucleic acid composition playing an important role in understanding the different types of microalgae?
Can you repeat your question, please?
So the question is how nucleic acid composition playing an important role in understanding the different types of microalgae.
Nucleic acid is not as such playing any role unless it will not join with the other components. But honestly, I am telling you, we have to do more research on the nucleic acid. They are not going directly affect to it because their content is lesser than the other, like the proteins, fats, or the carbohydrate. If you can ask is some easy way, probably I may answer because I am not able to understand what do you want.
Actually, the participant, I guess, is asking about the nucleic acid composition of microalgae. Is it varying in different types of microalgae? On that basis.
So, can I answer on behalf of Dr. Tiwari? I'll just try to add to that. Usually, microalgae, especially the unicellular microalgae, the nucleic acid composition ranges from 3 to 5%. The rest of the high products, biomolecules, are proteins, lipids, and carbohydrates. So that's where nucleic acids does not increase based on the microalgae or something. But the nucleic acids are the one which control what are the products which has to be formed.
Thank you so much, sir. The second and the last question we have for sir, that is, how does temperature play an important role in the growth of cyanobacteria?
Yeah. Cyanobacteria or any other eukaryotic algae, they desired specific range of the light. Light and temperature both are correlated to each other. And the cyanobacteria are the prokaryotes. So if temperature may go beyond above 30 centigrade, their secondary metabolites production decrease. Ideal temperature for the good growth of the cyanobacteria in culture condition as well as in the outdoor cultivation, between, ideal, I am talking about between and covering the range from unicellular to multicellular, ideal should be 25 to 35 degrees centigrade. It will depends on the organism to organism. But you don't think if X is growing maximum in 25, then again the same will not go grow in 35. So it will depends on the organism to organism, but ideal in range 25 to 35 degrees.
Thank you so much, sir. Last question we have that how harvested biomass how to harvest biomass for practical purpose in laboratory. If it is there any technique, please tell us how can I harvest easily, simple method. Actually, the
That's all
attendee
you
wants
have
to know the harvesting method.
You have to use. You can't get 100% harvesting, but you have to use using muslin cloth. In muslin cloth, if you are harvesting, you may get around 70% biomass, not more than that. And if you are putting 2 layers of muslin cloth, you may get around 75%. So in laboratory purpose, even for the small scale cultivation from the flask or from Hopkins flask or from the tub or from the bucket, we use only the muslin cloths, and it's easily available in the market.
Thank you so much, sir. Over to you, Dr. Pavan, sir. The questions are completed. Thank you.
Okay. Thank you very much, Dr. Tiwari, for your valuable time and talk. And I think it has enlightened all the participants the basics and also the relevance of how you can use algae and cyanobacteria in the labs to train the students. And also, it was an excellent talk. And I would, on behalf of AKS Satna and all the organizers, I would once again thank Dr. Tiwari for his time and great talk.
Thank you, sir. Thank you.
Thank
Professor
you.
Kamlesh. Professor Kamlesh.
Yes, sir. Thank you very much, sir. I was listening to you very precisely and.
Thank you very much. Thank you very much.
I have learned so many applications related with this algae. So not only we can use this for biofuel, as well we can use for many purposes like in agriculture. So I will try to give your lecture to our students also, that they can learn many things from that. How can we use this algae for different purposes in our area?
Yeah. Slide is available with the Dr. Pavan, so you can.
Yeah. Yes, sir. Thank you very much, sir. Thanks a lot, sir. Yes, sir. Pavan,
Please
sir.
share your mobile number too. Kamlesh sir.
Yes, sir. I will.
Please mail your mobile number too.
Yeah. I will.
I don't have your mobile.
Yeah, definitely, sir. Thank you, sir.
Okay, thank you. Thank you.
Yeah. I think Dr. Nikhil is available. So sorry, Nikhil, keep you waiting.
Yeah, good afternoon, sir. No problem.
Very good afternoon. So we are just running half an hour late. So sorry for that. And I think this is the last. I think participants. I think myself and Nikhil are standing between lunch. So sorry for this for all the participants also. I think this is the last talk for today's our workshop, 4th workshop. And Dr. Nikhil is assistant professor at Department of Biotechnology, Dr. B.R. Ambedkar, NIT Jalandhar. And he received a Bharat Ratna Kamraj Memorial Young Scientist Award from Kamraj University of Engineering and Technology from Madurai for his outstanding scientific contributions in the field of biofuels and biorefinery in 2019. He's also expert in bioenergy, biofuels, bioremediation and products, and biorefinery. I think I would like to say that the boss has started and the student is ending with the workshop. That's a great.
Really?
Very nice line.
Thank you. And and the floor is yours.
Yeah. Thank you, Dr. Pavan, and thank you, Dr. Kamlesh ji, sir, for giving me this opportunity to deliver this talk at this platform. The title of my talk would be Bioelectrochemical Systems for Bioenergy Generation through Waste Remediation. As rightly said by Dr. Pavan, that I'm a student of proudly I would say I'm a student of Dr. S. Venkat Mohan from CSR ICT. So yesterday he was the guest speaker, and I suppose he must have covered a lot of things, and out of which I would say maybe a decimal or a fraction of the part which I'll just try to present of it, which is my area of interest goes with. Yeah, so this would be the flow of contents of my presentation. I suppose I'm audible enough and also the presentation is visible clearly. If you have any doubts, you can please ask at the end of the presentation. So I would like to start with the introduction part of it. Yes, obviously it would be starting with the energy. So I would like to see from a top-down approach, basically on holistically in the global scenario of energy. It is this is the data from the Statistical Review of Energy in 2019. So this graph basically shows different sources of energy which has been actually used by the human population. And you can see largely it is the fossil fuel based energy that is undoubtedly it is the oil and the natural gas and the other fuels. But there is you can also appreciate seeing the thin stream of orange line, that is the renewable energy, which has been growing past maybe a decade or so, continuously giving us a futuristic hope that this would surely maybe not replace 100%, but maybe to larger extent it would really give us certain hope where we can use renewable energy. And that's why we are here all biotechnologists, that certainly again in renewable energy we have different forms of it discussed by the previous speakers. So yes, we have a different form. We will just see in the next coming slides. And this particular slide of graph which I want to share is that this is the global primary energy demand. This is also data taken from the Global Energy Outlook 2020 recent data reports. And this is the energy from different, and the timeline you can see here. And this is the 2020 data, and this is the historical graph line, which is the real-time data which has been actually taken. And these dotted lines of different colors indicate certain, projections made in the futuristic years to come, based on certain policies and certain, discussions made at different forums. This is basically quadrillion British thermal units of in terms of energy which is being discussed, and it is proposed that it is well known that there would be good amount of energy demand, but exceptionally they have certain maybe at certain cases where they have shown the projections to be going down. We really don't know at what criteria, because those are all completely empirical calculations, so we cannot exactly rely on that. But by and large, yes, it would, seeing to the current urbanization and industrialization scenarios, yes, there would be undoubtedly an increase or demand in the energy. And this is the the major consequence of the fossil fuel based energy society which we currently are running on, is basically the petrol, diesel, and the oil which we burn. So basically resulting into carbon dioxide, which is the major pollutant in one aspect, and also a greenhouse gas, right? And this billion metric tons of carbon dioxide which has been emitted. This is the trend line given up to 2020, and these are the projections again made by different forums and different policies. Yes, I know so many assurances you must have already heard or read in different news and platforms that yes, the new policies attempts have been made to reduce the greenhouse gases, majorly the carbon dioxide. If we are turning down at this particular projections, then it would be good news probably, because one way the global temperature also would be reducing to a certain extent. But not to be very optimistically, but pessimistically, if you see, probably there would be slightly rise in the carbon dioxide concentrations also. And this is the carbon dioxide concentrations. This is basically said as the Keeling curve data taken from the source, from the Mauna Lab Observatory in Mexico. Basically, it's present. So they continuously monitor the global carbon dioxide concentrations, and this is the data of the current data, which is very alarming. In fact, since last year, you can see occasionally there are certain publications and certain research highlights made at different forums of media, stating that the global, the carbon dioxide concentrations are beyond 415 ppm, which is really very alarming, and it is something which has to be really thought, and people like us are really working on how to make use of it. And yes, we have previous speakers were discussing algae as one of the options. Yes, but we'll see the carbon. Before I go into the topic, I have another series of data, that is the energy and water sector withdrawal and consumption, because I work basically in an interdisciplinary platform of treating wastewater as well as power production or energy generation. So this is the data again taken from International Energy Association. This is a bar graph which you can see at 2016 to 2030, forecasted 2030. And you have different, sources of energy. This is basically global water withdrawal in the energy sector by fuel type in sustainable development scenario. So basically, you have the primary energy of the fossil fuels, and largely the coal, which is the fossil fuels. So mainly and you have a certain orange fraction, which is the basically the power generation by the biomass, which is to be appreciated. And this is the water withdrawal. So it means that water which is used for by the energy sector. And like primarily, if you see by and large, whether it would be algae or majorly the agricultural biomass, which is by and large the source of biomass, production. So there is certainly, when you use agricultural biomass, so there would be certainly utilization of water also. So the clean water, what I mean to say, the clean water or groundwater utilization is taking place. At the same time, you can see here the global water consumption in the energy sector by fuel type. Basically, this is the energy basically utilized, and this is the water consumption data which is presented here. So that's what I'm just mean to say is that the blue part is the biofuels you can see here, which we are trying to project that biofuel, there would be a rise of biofuels, but certainly there would be also equally good amount of water consumption for the biofuels. So alternately, we have to see there, certain strategies we have to look out, that how we can, recycle back or maybe treat certain, amount of wastewater which is there, and also generate certain amount of energy as a kind of a contribution towards the renewable energy sector. And this is the data or the information stated by the World Bank, and basically it says that there is a crisis of both energy as well as clean water demand, right? So then we have a slide. Basically, I just want to say that water, energy, and climate as an access platform, we cannot exactly separate these three in different ways. The reason that if we try to utilize the energy that is the currently fossil-based fuel energy, so naturally there would be a scarcity and a demand happening in the society, and we have seen there is a water demand and utilization happening, and that in turn resulting into the carbon dioxide pollution because of the fossil fuel-based society, and then you have in turn affecting the climate change. Right, so these all three are interlinked, and we have to look for certain strategies, alternate strategies, where we can try to address this problem in a common, platform. And I suppose most of you can recognize this young girl who has raised her voice. Is Greta Thunberg. She's an active, volunteer in environmentalist basically, and in COP25, basically in Madrid 2019, she has been raising certain issues that carbon dioxide levels have to be reduced to a greater extent because of the after effects which we are seeing because of the global warming and other aspects. So with this brief introduction, I would like to go on to the topic of my research, basically, that is bioelectrogenesis. And bioelectrogenesis in a single crude way of understanding is bio is something with respect to life, and electrogenesis is something which is with respect to certain fuel cell or some electrode, and then genesis is something which you are trying to generate power out of it. So this is how the bioelectrogenesis is basically. So this is how the construction of fuel cell, right? You have an anode, you have a cathode, and you typically you can compare with that of the chemical fuel cell, and then you basically have these microbes, oxidation and reduction reactions happening, and basically you have oxidation at the anode, usually by a mixed consortia because we are dealing with waste, and then you have reduction reactions happening at the cathode, and when you close the fuel cell, basically you have the energy production, that is the bioelectricity generation which is happening. So this is a typical form of microbial fuel cell which comes under as a bioelectrochemical system. And we'll see the mechanism of it if you see of a microbial fuel cell. So you have the two electrodes here, and you have the bacteria, which is usually you have the membrane of the bacteria forming the biofilm of it. So you have the electron transfer. The main part of the microbial fuel cell is the electron transfer. And here the electron transfer you have in different modes, that is direct mode as well as indirect mode. In the direct mode, you have the electrons directly get transferred from the biofilm towards the electrode, that is the anode, while forming a biofilm over it. And whereas indirect electron transfer, basically certain bacteria, they need not form a biofilm. They may be suspended in the medium itself, and they might release certain chemical moieties like the Pseudomonas species, which are very familiar to release and under stress conditions, or probably so they act as a redox carriers. Basically, they carry the electrons, they shuttle and accordingly pass. And this shuttling is basically because of the difference in the potentials of the mediator and the electrode. And another recently they have discovered is that certain bacteria, they are said to be electroactive bacteria, like the Shionella species and the Geobacter species, and furthermore species are being explored yet, but these are very very commonly mentioned. So they have certain pili-like structures or hair-like structures, which are referred as the nanowires. And this is one of the hot topic of work which is going on. I will be discussing about nanowire soon in the coming slides. So basically, when you have metabolism here, so if you give, suppose for example, glucose as the substrate, and when upon breakdown of the substrate, basically you have protons and electrons releasing. And these electrons basically they are shuttled towards the electrode because of the difference in the electropotentials, right? And you have the cytochromes, membrane-bound cytochromes, and transport proteins which are involved in this shuttling. And also, to maintain the charge neutrality, there is proton pumps also, where you have the efflux of the protons out of the cells. And this, when you have in terms of a fuel cell, that is when you separate anode and a cathode using the proton exchange membrane. So basically they are sulfonated in nature to basically have better charged, you pre-treat the membrane basically, and so they get sulfonated charge, so that more and more protons are actually driven from the anode side towards the cathode side. That's the basic purpose of the sulfonated groups. And here once you get the protons over the cathode side, and when you close the fuel cell, basically there is an electron motive force being generated. So the electrons start driving because there is a difference in the potential. So electrons start driving from the anode towards the cathode, and at the cathode surface you have in presence of the protons and the oxygen, undoubtedly when you have exposed to the air, or you can also use a air pump, and accordingly you can provide oxygen, so undergoes a reduction reaction, and thereby there is a power being generated. And of course you close the circuit using under load certain resistance, so as to measure the the power measurements. You are not supposed to short circuit it, because the basic electrical principle says that you have to measure under the resistance. So that is a basic electrical principle, Ohm's law. Right. Next, I would like to show you the interfacial view, like how in a chemical engineering point of view, probably you can see the triple phase boundary that is being formed here. The triple phase boundary is that the solid, liquid, and gas. The solid is the electrode part, liquid is the medium, and the gaseous part is the electrons and the protons, which are basically involved in this process for the electricity generation. And you have, this is the one of the schematic diagram of the schematic of the membrane-bound proteins of Shimala species, which was widely cited, proteins which are involved in the shuttling of the electrons. And this is the basic, energy driving formula. Basically, the change in the delta E, that is the change in the energy, is equal to the standard potential of the cathode potential minus the anode potential. So greater is the gradient, and greater is the the energy that is can be harvested. With this, we'll move on to the other part. That is, this particular diagram is the PERT diagram that shows the the criteria for sustainable bioanodes. So, knowing the mechanism and the concept of the microbial fuel cell. So the major part you have come to know that it is the anode, because there the actual biofilm is formed. So this particular diagram will tell you the what are the criteria that the engineers have to actually look on to increase the current. Ultimately, it is the current that if you increase the current or the voltage, eventually the power production will be improved, because that is the our bioenergy part of it. So here, if you see, they are like the structure design can be modified. Basically, you can increase the porosity, pore shape, pore size, and you can we have a more macro porosity basically for the accessibility point of view, right? And you can have surface design modifications, like conductivity can be changed, roughness can be increased, right? Biocompatibility can be made using some different materials, and porosity is usually microporous in nature if you want to take certain materials, and hydrophilicity basically to increase the biofilm formation over it, and then you have charge storage. So if certain materials they have the property to store the charge, because the microbial fuel cells, as we proceed, I'll let you know. So basically, it is not only the amount of charge which is generated, sustainability also counts. So sustainability comes only when you engineer or you have a better, better fabrication of the reactor, and it starts from the electrode system. If those electrodes are designed such a way that there is certain possibility of charge storage, then probably there would be certain sustainability as well. And finally, modifying the area or design, finally it leads to high volumetric current density. This is what is basically aimed. Volumetric, we talked in terms of volumetric current density, means the scale up of the volume of the reactor. Maybe for the lab purpose, we run it for 100 ml, 200 ml, or maybe up to 1 liter of reactor size. But if you start scaling up at the industrial level, so would the energy density remain to be higher or not? So yes, we will, as we proceed through the sites, we'll get to know certain more information about it. Yeah, having said about that, this is one picture which I want to say that what makes me fascinated to work on microbial fuel cells or the bioelectrochemical system tells us that it's a multidisciplinary challenge. All science and engineering background people are required to work with this microbial fuel cells or the bioelectrochemical systems. So you need to have certain knowledge about the microbiology, obviously, because we work with the microorganisms, and you have certain potential for the material science people, basically because you use the electrodes. So as I told in the last slide, having biocompatible electrodes, which having different specific properties like hydrophilicity and porosity and charge bearing capacity, and such kind of features can be actually brought by the material science people. And certainly the certain design engineering aspects is required by the maybe the chemical engineers or the mechanical engineers also can be working out, like what is the distance of between the electrodes that has to be placed, and whether the membrane has to be placed or not, what kind of membrane can be used, what ways can be employed to reduce the cost of the membrane, alternative membranes for the microbial fuel cells. And obviously there is an electrochemistry involved in it, because it's a fuel cell. So you have to know that the redox reactions, how the redox reactions are taking place, and where the electron from which channel the electron is transferring from either it is from this end to the other end or the vice versa for that matter. And of course, certain electrical chemistry is to be known, because the product what is being formed has to be analyzed at the end of the day, and that product should be desirable and have societal importance also. So such kind of products can be also harvested using a microbial or the bioelectrochemical systems we'll be seeing soon. On an environmental perspective, yes, if you are using wastewater as a substrate, so it is also addressing the environmental perspective. So like this, you have several science as well as engineers working in a consortia. Then only you will be able to come out with an fantastic solution of bioelectrochemical systems or the microbial fuel cells for the power generation aspect. Yeah. So as I was discussing earlier, nanowires. So this is one of the hot topic of research which is actually going on in many parts of the, I would say, Europe and US. But in India, I think I have not come across many such groups. But yes, very seldom. Even my group at Dr. Swangan Monsarlo, we were an attempt to study on nanowires. But then it requires a lot of instrumentation and facility. And I suppose, I don't know, it is almost quite 5 years that I left the lab, so I don't know the current situation in the lab that they are working the progress of the nanowires. But surely, yes, we had certain objectives that time. So by and large, what are nanowires? Nanowires are basically, these are conductive appendages, hair-like or pillar-like structures, basically. And as I told, it is found in the genre of Geobacter and Shivella species, and they are basically found. These are certain species names. So these are pillar-like structures. So usually their functions are for adhesion, movement, and biofilm formation. And recently they have found that there is an involvement of these pillar-like structures for the conduction or the transfer of the electrodes that is happening. And the mechanisms which they have cited is that two mechanisms they have cited. One is the pillar-like structures are basically like acting as a wire, which is like having metal-like conductivity properties, where the chemistry behind it is the overlapping pi orbitals between the atoms, which are allowing to actually share the electrons freely. Alternatively, there is another method which has been proposed by electron hopping method. Because of the presence of the iron heme proteins, the electron is getting transferred from one end of the pili structure to the other end of the pili structure. Because of the, again, there comes the potential difference between the anode as well as the bacterial pili which is there, the protein. So accordingly, the electrons are hopping, and that's how they go. And other bacteria which was also cited in the literature, which I want to present, is Desulfobulbaceae bacteria. These bacteria are basically found in the sediments of the seas and ocean. So these are very commonly called as cable bacteria because they form very long cables, and they are found that basically these bacteria, they oxidize the hydrogen sulfide which is present at the sediment, and that's how they get the source of energy. And in the process, during using the periplasmic membrane space, you can see here the dots showing the movement of electrons, how they go to the pass through the cables. And these are certain microscopic images in the fluorescent images showing how the the cables which are glowing under the microscope. These are research is going in this on these using these bacteria as well to use as a microbial wires. More exploitation is going on. There is one or two groups in the Europe, I guess, who is working extensively on the cable bacteria. Okay, having said about the principle and the potential of nanowires and all, so we will be all excited that there is a good amount of energy being generated out of the microbial fuel cell. But there are certain other factors which we need to look on, that in a usual typical fuel cell, suppose you close the anode and cathode, it is expected that if it is an ideal situation, then the voltage should not drop at all. Ideally, it should not drop at all. But then in a realistic situation, what happens is that there is a drop of voltage which we can see here. There is a voltage drop happening, and this drop in voltage is because of several reasons, and which is usually cited as activation loss, ohmic loss, and concentration losses. Just a second. Yeah. So basically, if you see the graph, you have the x-axis as the current density, and y-axis is the cell voltage. So when you ramp it against a resistance, as I told you, so when you usually measure a power, so you have to close the circuit under a resistance. When you close the resistance, so there is certain this kind of behavior. This is called as a polarization curve. And that polarization curve, you use different resistances, variable resistor, and accordingly you plot this particular graph. And these are the losses, activation losses, ohmic losses, and the concentration losses. And it is found in the literature there are several factors affecting these losses actually. It is not only the mere resistance that has been applied, there are certain factors like maybe the type of electrode, nature of electrode, conductivity of the solution, substrate, affinity of the substrate to the microorganism, and formation of biofilm, thickness of biofilm formation, right? Mass transfer between the substrate and the microorganism. So there are so many sorry factors that are actually responsible for these losses that is being displayed here. So to assess the performance of the fuel cell, and there are certain analysis which are very commonly performed. Yeah, these are certain analysis which are commonly performed. This is how a typical a fuel cell looks like. You have a biofilm here, and then you have anode as a reference. What do you say? As a working electrode, and then you have a counter electrode as a cathode, and then you have a reference electrode like a silver chloride electrode, basically. That is for the reference electrode. This is the 3 electrode system. Basically, you connect it to a potentiostat to measure the voltage differences, and obviously you also make conductivity measurements basically, and you make sure there is a good amount of conductivity between the 2 electrodes, anode and cathode. Maybe sometimes you can use a reference electrode as both reference as well as counter electrode, or sometimes you can also use the cathode also. And then you have a cyclic voltammogram, or the cyclic voltammetry is a technique which is also commonly used. So this is the typical cyclic voltammogram, which usually you get it for a chemical system basically. So if you have a perfectly redox system, so this is how you get the cyclic voltammogram, where when you oxidize and then you reduce it, you get the peaks, and these peaks are referring to the electron transfer happening, and these peak currents are basically used for certain calculations and in electron kinetics, and this is the potential where you basically ramp like from minus 0.5 to plus 0.5, or maybe in the positive side also, maybe from plus 0.1 to plus 0.5 or minus range as well. It all depends on the the reactor conditions, where you want to basically target, which electrode which you like to target is also product based also. So these are certain techniques. So this also applies not only for the microbial fuel cell, for the bioelectrochemical system, any bioelectrochemical systems also. Based on this analysis, you get if you try to take this particular graph and try to make a plot using there are certain options to make a TEFL flow based on the sweep voltammetry which you have. This is the if you're taking both the curves, anode and cathode, it's cyclic voltammograph. Either if you take a single sweep, it would be a linear sweep voltammetry. And this linear sweep voltammetry is basically used for calculating the TEFL slope and the TEFL plot. Basically, this is how you get the TEFL graph. And using the Butler Volmer equation. Basically, you calculate the activation losses. You calculate the activation losses, and based on the change in the currents, and this will give you the data how much activation losses are present in your system, and further losses like the mass transfer losses and the other kinetic losses. This is another technique called as electrochemical impedance spectroscopy. This is a very sensitive technique, and basically in this technique we try to apply certain frequency. Usually in chemical systems we apply large frequencies, but then for biological systems it is advised to use at very low frequencies, because the biofilms are very sensitive to certain these frequencies which you are trying. So you apply certain frequency, and accordingly you measure the resistances. Okay, so this is how the plots which you get. So this is the resistance in the real axis versus the resistance in the imaginary axis, and basically you get the graph in this way, and you need to fit with the circuit, appropriate circuit. There would be an options displayed by the customized software which is attached along with the unit, spectroscopic unit. So that will tell you at what circuits, if you fit particular graph, you would result with the mass transfer control data, as well as the mass, the kinetics of it. Then you have about the energy distribution. Basically, there was a literature report made by Stanford University way back in 2013. So here they would say they were citing that whatever energy substrate in the form of substrate carbon source which we give, is it actually all that substrate is being utilized in the microbial energy generation? Means it was observed that they have empirically calculated, and they found that certainly not. There would be only 20 to 30% of net electrical energy produced, because these are the different losses, possible losses, where the actual chemical energy input which you have given in terms of the electron donors, basically they get reduced down the lane, and these are the reasons for the losses, or these are the reasons for the electron losses. So attempts are made by the different groups, people working very actively to reduce these losses to better extent, so that the net electrical energy is being improved. Sorry. Then you have the strategies for increasing the power output of microbial fuel cells. So there are certain strategies being proposed in the literature. Basically, you can increase the anode performance, enhancing the anode performance. You can use these are the strategies like mediator immobilization, carbon surface modification using nanostructures, metal surface modification, 3D architecture, etc. Or you can also use optimizing separators, like people working with the membranes can come out with a good separator where it is porous or gel-like substances, and you can also decrease the internal resistances by changing the electrode resistance, assembly, distance between the electrodes, media, the ion strength of media, and all. You can also alternatively enhance cathode performance, because it is not only, people have found the literature that it is not only the anode, it is also the cathode also plays a major role, because end of the day, once the electron cloud is being formed at the anode, if there is no potential gradient at the cathode, means if there is no good amount of reduction happening at the cathode, so there is no use of concentrating electron cloud at the anode itself. So if there is only gradient only, then only effectively there would be a power generation. People started also working with the cathode performances and using basically high oxygen reducing catalysts, basically like platinum based catalysts, and there were some certain biocatalysts also used. And here alternatively another strategy which can be used, especially when you are looking for a scale up operation. So usually we do the serial stacking. So stacking, either we can connect the circuit in series or parallel, to accordingly look for max good voltage or current depending on the type of application we are looking for. But when you stack the cells, microbial fuel cell, it was observed that there's a possibility of voltage reversal happening. Even though you have a very similar, microbial fuel cell of same construction, same material, same volume, same amount of inoculum, everything same to same. In spite of that, also there would be differences in the potential generation or the current generation. There would be number of reasons for that. So they have observed when you connect these two cells either in series or parallel, so the cell which is having lesser voltage or something, lesser current or for that matter, so the electrons start going reversal instead of going into the circuit for the power generation. Rather, they try to balance the other fuel cell which has having the lesser amount of electrons or the voltage. So to minimize that voltage reversal, several people from the electronics background, especially, they design certain circuit chip boards and certain algorithms are written basically to make sure that whatever electrons are being produced are driven properly and power is collected to the maximum extent without reducing the voltage reversal happening. Yes, there are other groups also working on this exclusively from the electrical EC electronics background people working on this direction. So this is my research outlook which I have been worked on, and this is also one of my layout of research which I'm basically work on. So I work on different platforms like acidogenesis platform, bioprogenesis platform, and biofermentation platform. So this is nothing but an extension to a microbial fuel cell, where you use that for a different resource recovery part of it. So these were certain aspects which I worked on during my doctoral studies at IST. This is one of the new review paper which you must have seen probably yesterday as well. My supervisor must have presented. So this is basically a microbial electrochemical systems with multifaceted applications. You have microbial fuel cell and then electrochemical treatment cell, electrochemical systems, my MECs, microbial electrochemical cells, microbial desalination cells. So it all depends on the type of application which you are looking at, and these are the possible inlets, source of feedstock materials for these particular systems to run. So I share certain amount of research data which during my doctoral studies which I've performed. So basically I've taken certain microbial fuel cells constructed there. I'm really grateful once again. I would like whenever I present these slides, because it was great efforts put by me as well as guidance from my supervisor, and also I would like to thank the workshop at ICT. We were really fortunate to have inbuilt in-house workshop fabricating such kind of fuel cells at ICT itself, and I have basically done an experiment to see that what resistance basically you get a maximum power production happening. So we have done a polarization study, and we got to know at one particular resistance, say 200 ohms, we have got at these fuel cells, small fuel cells of maybe 100, 150 ml of capacity. So at this particular fuel cell, at 200 ohms, if you close the circuit, you would get a better power. And that we wanted to test it for a long-term study. So we have done long-term studies, and accordingly, we have observed that yes, if you run the fuel cell at maximum power, at the power point, maximum power point at 200 ohms, if you close the circuit, then you will able to get a better power production at at this particular condition. Further to that experiment, we have supporting analysis experiments were also done. Basically, we carry out anode potential also. So basically, this anode potential will tell you that how much amount of the health of the anode, basically, that is biofilm formation over the electrode. So greater is the anode potential in terms of the minus potential. So greater is the anode potential, better is your biofilm being formed, or better anode cloud which is being formed. So it depends on again the electrode material. So we have used initially graphite, and later on, as I proceed the slides, there were certain variations in the electrodes also. And I have also, based on the study made by the Stanford, I just had an curiosity to do the similar kind of empirical analysis even in my systems. So I also found a similar kind of performance, that hardly only 15 to 20% of energy is actually involved in the electrical energy production for the amount of substrate. So here we have used a design synthetic waste with carbon being glucose as a carbon source. So which is very giving very less amount of the yield, which is coming to 20%. So we've also done certain other analysis, supporting analysis, that are polarization analysis also for the fuel cells. So these are the voltage graph, polarization graphs, and the power graphs. So basically we have carried out certain slope measurements, empirical analysis, to find out what losses are basically employed in it. So it is the concentration losses which is dominating, and we have certain amount of ohmic losses and the activation losses. So the concentration losses, the major factors which are affecting the concentration losses is the biofilm formation. So if there is a thick biofilm formation, so there would be a hindrance of mass transfer, aspects come into picture, where the substrate doesn't penetrate into it. So probably in this, maybe all the 100% of energy is not actually going conversion, only it is utilizing only it's for its metabolism and maintenance, but not for the energy production. Later we continued changing the electrode and see how the performance varies. So in one of the cell we have taken only graphite, and in one of the cell we have taken the carbon cloth as one of the electrode material, and in another graph we have basically taken carbon cloth coated with carbon nanotubes, were doped over that particular carbon cloth with material, which is also conductive in nature. And then we have changed the buffer conditions. In this fourth one, we have same graphite electrode only, but only the buffer conditions at the cathode was changed. Unlike in these three cells, we had water, only distilled water sparse with oxygen, whereas here we have taken a buffer, phosphate buffer sparse with the oxygen, just to make sure that is there any role of the buffer over the performance of the fuel cell. And these are certain polarization studies being carried out, and we have observed that the fuel cell operated with the carbon nanotubes, it's carbon cloth coated with carbon nanotubes, resulted in a better fuel efficiency, better maximum power, as well as the current aspect as well, and compared to the other conditions which we have taken. I've also performed certain voltamograph studies also, cyclic voltamographs. So at the CNTs, using CNTs, there are good amount of electron transfers using redox transfers were also noticed here, because the electron shuttling was good enough using the CNTs. And this is with respect to the graphite, with respect to the buffer solution, and with respect to the carbon cloth. And if you see the currents, oxidative currents and reactive currents, actually, it is the currents are higher for the CNT case, in case of the CNT. So that was with respect to the microbial fuel cells, a certain fraction of data which I have showed you. And I've also worked with certain other aspects of this fuel cell, that is the microbial electrolysis. This is a kind of a bioelectrochemical system where we try to harness hydrogen, mainly hydrogen. Alternatively, you can also look for methane. There are studies for methane as well. But in my study, I have looked for the hydrogen production, basically. So my objective, as I worked with Astrogenesis platform also, after biohydrogen production or the anaerobic digestion, basically, cannot prolong it for a long time because there are acids being formed. Those are short chain acids or the volatile fatty acids. So these acids, from the wastewater treatment point of view, if you see, after anaerobic digestion, only 30 to 40% is actually, and of the total organic matter is actually remediated, and certain fraction comes out to be the volatile fatty acids. And these volatile fatty acids, if it can be further consumed to form the hydrogen, was this particular objective of this particular study. So what I have taken a system microbial electrochemical system where I have had a bioanode as well as a biocathode point of view. Related to this literature before my work, there were publications on abiotic anode. Means they used to take platinum electrodes here and accordingly maintain abiotic condition, and or maybe abiotic cathode condition. Either of these would be abiotic condition. But I tried something differently with a biotic cathode and a biotic anode both simultaneously. So here I have taken glucose as a substrate, which upon fermentation results in the short chain acids. And after a 24 hours period or 12 hours, whatever the condition which I have taken, so this turns out to be the volatile fatty acids. And these fatty acids were given as a substrate at the cathode chamber for the hydrogen production. So there was a mixed consortia. Basically, I've used the same source, that is anaerobic inoculum, but the electrode, the system was run for long time periods, basically to make sure the specific consortia, starts, forming a biofilm over it. That is also a mixed consortia. Actually, this consortia, anode consortia and cathode consortia, are after analyzing DNA analysis we have sent for sequencing, and we have found there's a difference. But the data I don't have as of now. But there was the group analyzing with under my supervisor only for the exclusively the molecular biology aspect of it. So we found that there was a difference in consortia because of the electrochemical conditions which we are worked on, the reactor conditions which we worked on. So we apply certain potential here. So these are certain the potentials which I applied in my study was 0.2, 0.4, 0.6, 0.8, and 1. And above 1 potential reduction potential, basically, certain water electrolysis was observed. So this is the gas composition. Basically a mixture of hydrogen as well as the carbon dioxide was observed, and this is the total biogas, which is about in terms of volume it is 200 ml, and the percentage which is containing up to 70 to 80% is by gas chromatography found that this is the amount of hydrogen, and this is the amount of 60% is about hydrogen, and 20 to 30% is about the carbon dioxide, and rest maybe the trace gases, right? And another interesting part of this particular study was the buffering capacity analysis, which we performed using an autotitrator. So we believe that these volatile fatty acids are basically weak acids, and the weak acids have a property of showing the basic property is for a wastewater should be the alkalinity. It has to have certain resistance to the change in pH, irrespective of the presence of the short chain acids. So using this buffering capacity analysis, these peaks were observed, and these peaks represent to the pK value, that is the acid dissociation constant of that particular acids, and majorly it was acetic acid. If you compare the pK value around 3.75 or around such value of acetic acid, and the peak area is directly proportional to the concentration of that particular acid which is present in the solution. And it was observed that at point 6, which we have observed good amount of loss of the acid which is happening. It means that utilization of acid towards hydrogen production. That is the inference which we get from this particular graph. And this is the mechanism similar to that of the microbial fuel cell which we have, but this is over the cathode side. So similarly, you have a different cathodic consortia, where again there are certain membrane-bound proteins which are responsible in taking the electrons from the cathode, because the electron comes from the anode to the cathode. The cathode, from cathode, it enters into the cell, And inside the cell, then you have the periplasmic space, and you have the hydrogenase enzyme. And this hydrogenase enzyme is actually responsible for the production of the molecular hydrogen. And this particular hydrogen is actually what we are trying to calculate and estimate it. There are certain dehydrogenases also responsible for the metabolic activities, phenone pools, and this is the membrane bound chemistry which is actually happening. So this is finally you get up to the hydrogen, which is the product of interest. And certain other studies also we have carried out to our curiosity to find out what if we design a reactor where both simultaneously electricity as well as hydrogen production can be noticed. So this is one of the reactor again fabricated in our lab, and we try to remove the membrane to reduce the cost economics of the reactor and see how would be the performance of the reactor as well. Yes, the performance of the reactor in comparison with the membrane-bound reactor reduced to a certain extent, but yes, the performance was not that drastic, but notable amount. So here we just try to change the conditions of circuitry basically. Try to take a similar kind of a cell with a run through an open circuit. Then we had a short circuit, which without the resistance, which is usually not recommended. But we just tried to make an understanding what if it is short circuited, and then you have a closed circuit under the resistance of 300 ohms. So since the reactor configuration is different, so we again performed the polarization study, and accordingly we found 300 ohms to be the optimum load for this particular reactor. So accordingly, it was closed at 300 ohms. And this is the biofilm over the graphite electrodes. You can see how the biofilm was found at a greater extent at the anode in comparison to a cathode, relatively less, because we didn't use any membrane. A certain amount was formed at the cathode also. We have certain measurements made in terms of open circuit voltage. Yes, there was a voltage, open circuit voltage. It means that without connecting the resistance, you are measuring only the potential difference between the anode and the cathode. So there is good amount of potential difference observed. And for the power density for the fuel cell, which we closed using the 300 ohms of resistance, yes, obviously there is a power production as well. The product of voltage and current will give you the power values. And this is the hydrogen production also was hydrogen production was noticed. And the reactor operated with closed circuitry, that is with 300 ohms, resulted in better hydrogen production in comparison to the other circuit mode of operations. So I have done certain empirical calculations based on the formulae available in the literature, which was well cited. So we have done certain yield calculations, and we have found that when you have a closed circuitry, then there is a better hydrogen yield per kg of the COD removal in terms of the wastewater treatment aspect. So you are more responsible for the COD removal data. So this would be optimistically better. Alternatively, we have also seen that the electron distribution, how the electrons are basically distributed for what kind of component. Is it charge distribution, or is it for hydrogen production, or was it for the biomass formation? So for closed circuit operation, we have seen a greater fraction of electrons are basically going for the charge, that is the electricity power production, and certain other fraction for the hydrogen production, and very minimum amount of fraction for the biomass formation, which is usually desired for any kind of a electrochemical system, because we not intending more of biofilm formation, but a certain amount of biofilm is required. Once the biofilm is formed, covered through the surface of area, then it is not interested to have thickness of biofilm, because again mass transfer effects come into the picture. So that was the object, work of the simultaneous electricity as well as biogas, the hydrogen production. That was that work. Another work which I performed was microbial desalination. using a 3-chamber electrode system. So this was also done for the first time in our lab. So basically, we have taken, unlike a 2-chamber, we take a 3-chamber. The basic purpose of this desalination is most of the water which I told you. So it is a clean water is very less amount of clean water you have in terms of rivers and lakes, and very you know very well what is the situation of the clean water. So majority of it is 70-60.
Sorry for that, because it was so interesting. I don't want to stop the talk because the opportunity rarely comes. So I would first of all thank Professor Kamlesh Chauri for organizing this workshop on behalf of AKS University, and it's actually a breathtaking exercise. And we have listened to number of speakers in the biofuel area, different aspects and expertise of their in terms of not only science but also students or a faculty can assume how a basic science can be translated to industrial. So this is where the government is pitching Atmanirbhar. So that is where I think if you can pull all the talks and put it together, you have from basic science to a translational research where everything can be coupled, and it gives a meaningful event where everything can jolt a beautiful future in biofuel area. So especially for students who are very much interested, because biofuel is an area which is going to start in next generation. And we have to have an alternative for a future, because we cannot just start once the problem starts. So we have to look for all the events. And I would like to thank all the speakers, eminent speakers, especially Professor S. Venkat Mohan, Dr. Reena Pandit, Dr. Vivekanand, Dr. O.M. Tiwari, and Dr. Nikhil for their outstanding lectures and talks regarding their work. And I think all the eminent people are available for the students and the faculty who are interested to collaborate. I think on behalf of everybody, I also just trying to put on that because most of them may be very happy to collaborate on behalf if anybody is interested. And once again, I would like to thank Professor Chauri and the AKS University management for organizing such workshops, which will actually enrich the knowledge of ongoing research throughout the country to all the participants. So as a convener, I'm just finishing my task. So over to Dr. Chauri.
Thank you very much, sir, and I must congratulate to you and for your path-breaking lecture, and because the related work you have elaborated here in this workshop is very nicely explained. Organize that event with the help of you in the professor. So thank you very much, sir. Thank you, Arpit, Vivek, Saurabh, Shreyans, and my whole team. You are doing very great job with us to make it successful. And once again, thank you everyone. And if some words you want to say, Pawan Juthur sir, so I also again request you to conclude this session, and we will close it. Thank you, sir.
Also I would like sincerely thank all the speakers for the effort and time, and I think you can have a feedback section from all the participants. So in future, if we want something, because I think this as a theoretical this thing, it's very interesting. So because of the COVID situation, we cannot have a practical section. But I think in future, as you said, like once we are meeting at AKS, we can definitely plan for a hands-on workshop, which will fascinate the students how to learn simple things in a better way. So especially with, I think Nikhil also agrees with this because there are some kind of new things which the students can get new ideas to generate those things. So once again, I would like to thank all the speakers and AKS University for organizing this and wish all the best in future. And thank you.
Thank you, sir. Now
Thank
we
you,
are
sir.
closing
Thank
the
you.
session. Thank you.
Thank you, sir. Thank you.
Thank you, Nikhil.
Bye bye.
Yeah, thank you.
Thank you,
Bye,
sir.
sir.
Excuse me, sir. There is a small announcement for all the attendees that all
Yes,
the
sir.
attendees please be very careful that you will receive a feedback link for this session by today evening, and we will like to welcome you all in the workshop number 5, that is on the fermentation technology. The convener of this program would be Dr. Vivekanand from the Center of Engineering and Environmental, Malvian National Institute of Technology, Jaipur. So we'll meet you soon on 17th September. Till now, then we are signing off. Thank you so much.
Thank you.
Thank you, sir.